At the edge of the universe, where light has traveled over 13 billion years to reach us, faint blue galaxies flicker like cosmic whispers. They're not just ancient, they're mysterious, defying everything we thought we knew about the early universe. Why are they so blue? So distant? And what secrets do they hold about the birth of stars, galaxies, and time itself? What you're about to hear may reshape your understanding of the cosmos forever. But before we continue, subscribe to the channel so you don't miss out on any of these videos. That question has haunted cosmologists for decades. And what if I told you that these unassuming smudges of blue might hold the key to some of the biggest mysteries in the universe? That these barely there galaxies are rewriting our understanding of time, structure, gravity, and even how the cosmos began? Stay with me. Because we're about to journey across space-time, from the moment the first light escaped the Big Bang to the ragged shores of the cosmic horizon, and beyond. We'll explore the invisible scaffolding of dark matter that helped shape these galaxies, the powerful telescopes that first glimpsed them, and the paradoxes they pose to the standard model of cosmology. We'll dive deep into the physics of star formation, cosmic redshift, gravitational lensing, and how the faintest light from the earliest galaxies may answer one of the most profound questions of all time: why is there something instead of nothing? But first, let's step back, not just in space, but in time. Billions of years back. The observable universe is a strange concept. Most people picture it as a sort of spherical shell, 46.5 billion light-years in every direction from Earth. But that's not quite right. Because of the universe's expansion, some of the galaxies we can see are actually much farther away now than their light travel distance would suggest. When we say, observable universe, we're referring to the limit of what light has had time to reach us since the Big Bang, about 13.8 billion years ago. But because space itself is expanding, the current proper distance to those sources is vastly greater. Now picture this, deep in that edge zone, a place so distant we're seeing it as it was less than a billion years after the Big Bang, astronomers began to notice something strange. The first real hints came in the 1990s, when the Hubble Space Telescope was pointed at what seemed to be an empty patch of sky. This now legendary experiment, the Hubble Deep Field, changed everything. Instead of blankness, Hubble revealed thousands upon thousands of galaxies, each one a sprawling city of stars. But some of these galaxies were odd. They weren't grand spirals or bloated ellipticals. They were small, irregular, dim, and blue. And there were a lot of them. Astronomers expected to find some early galaxies, yes, but not this many. And not like this. These faint blue galaxies didn't fit the mold of slow, hierarchical growth models. They looked like snapshots of a cosmic era that seemed to move much faster than anticipated. The blue color was especially intriguing. In astronomy, blue means young. Hot, massive stars burn blue, but they don't live long, only a few million years. So blue light in these early galaxies meant fresh, intense star formation was happening just a few 100 million years after the Big Bang. But how? The early universe was supposed to be chaotic, filled with opaque hydrogen gas that hadn't even cooled enough to allow stars to form freely. For stars to ignite, for galaxies to coalesce, a certain level of order and cooling is required. Yet here were these primitive systems already thriving, shining through the veil. These galaxies began to earn a nickname. Faint blue galaxies. The name is simple, but it disguises the incredible strangeness of what they are. So what do we know about them? First, they are faint, so faint, in fact, that many of them are at the very edge of what our most powerful telescopes can detect. And it's not just their distance that dims them. It's also their size. Many of these galaxies are compact, far smaller than modern spirals like the Milky Way, and made up of only a few billion stars. By comparison, our galaxy has hundreds of billions. Second, they are blue. This is a massive clue. Blue galaxies are rich in young stars, which are born in dense clouds of hydrogen gas. That means these galaxies are active, they're forming stars, they're evolving. And that's weird. Because at these redshifts, these extreme distances and times, we didn't expect to see such maturity. Third, they are everywhere. The number density of faint blue galaxies in deep field surveys is staggering. Far more than models predicted. The Hubble Ultra Deep Field, the Good surveys, and now the James Webb Space Telescope, all have confirmed it. The early universe wasn't a slow trickle of formation. It was a frenzy. So let's talk about why that's so important. The current standard model of cosmology, known as lambda cold dark matter, or lambda CDM, predicts that small structures should form first, merging over time to create the massive galaxies and clusters we see today. This model has been wildly successful in explaining large-scale structure and cosmic microwave background measurements. But it stumbles a bit when it comes to these early faint blue galaxies. Why? Because they seem to be too evolved too soon. Some of these galaxies are forming stars at incredible rates, 10, 100, even 1,000 times faster than the Milky Way today. That means they've somehow gathered enough cold gas, created gravitational wells strong enough to hold onto it, and triggered intense starbursts, all in a universe that was less than 1 billion years old. Something doesn't add up. And so began a new line of questioning. Maybe these faint blue galaxies are revealing flaws in our simulations. Maybe we've underestimated how quickly gas can cool and collapse in the early universe. Or maybe, just maybe, something more fundamental is going on. Dark matter might hold a piece of the puzzle. These early galaxies could be forming in dense knots of dark matter, the mysterious, invisible substance that makes up about 85% of the matter in the universe. Dark matter doesn't interact with light, but it does create gravity. And that gravity could be pulling regular matter into place fast enough to explain the burst of early star formation. But then there's the question of reionization. Between 300,000 years and about 1 billion years after the Big Bang, the universe entered a period called the Dark Ages. The first atoms had formed, but stars had not. The cosmos was filled with neutral hydrogen, a fog that blocked ultraviolet light. Eventually, as the first stars and galaxies lit up, their radiation began to ionize this hydrogen, turning it transparent. This was the epoch of reionization. Faint blue galaxies may have been the culprits. Their intense ultraviolet output, driven by vigorous star formation, may have been enough to ionize vast swaths of hydrogen, ending the Dark Ages and making the universe transparent. If that's true, then these humble-looking galaxies played a pivotal role in making the modern cosmos visible. But there's more. Much more. With the arrival of the James Webb Space Telescope, JWST, the game changed yet again. Its infrared capabilities allowed it to peer even deeper, through dust and across redshift, to the true edge of the observable universe. And what it found was astonishing. JWST has revealed hundreds, possibly thousands, of candidate galaxies at redshifts beyond 10, meaning they formed just a few 100 million years after the Big Bang. And many of these are, yes, faint blue, irregular galaxies. In fact, some of them appear to be forming stars at rates impossible under current models. It's triggered a quiet panic in theoretical physics. Are we missing something about how early the first stars and galaxies could form? Are our assumptions about dark matter wrong? Is there a new physics at play in the early universe? And yet the data is real. The light is reaching us. And those galaxies, improbable as they seem, are there. So let's go further. Let's imagine what it would be like to actually travel to one of these faint blue galaxies. Not in a spaceship, that's impossible, of course, because of the distances involved, but in a thought experiment. Picture a galaxy, compact and chaotic, just 500 million years after the Big Bang. The stars are young, massive, and unstable. Radiation floods the interstellar medium. Supernovae detonate constantly, recycling material and driving turbulence. There are no familiar spiral arms. There's no elegant structure. But there is life, in a cosmic sense, raw, unrelenting creation. These galaxies are laboratories. They offer us a chance to study star formation, chemical evolution, and black hole growth in conditions completely unlike today's universe. And they challenge every assumption we've made about how galaxies evolve. The question becomes not just what these galaxies are, but why they exist in such numbers, such brightness, such eagerness, at a time when the cosmos was still a baby. And what if these faint blue galaxies aren't the beginning of something, but the echo of something before? These faint blue galaxies are not simply distant. They exist at the very edge of what is physically observable in the universe. That means the photons reaching our telescopes right now started their journey not long after the Big Bang itself, when the universe was just a few 100 million years old, a mere infant compared to its current age of 13.8 billion years. These galaxies are small, often only a fraction of the size of our Milky Way. But despite their size, they are disproportionately active. Their blue color indicates intense star formation, meaning they're producing hot, young, massive stars at an incredible rate. That's the first puzzle. According to our best models of galaxy formation, the early universe shouldn't have had enough time or the right conditions to form galaxies like these, especially in such high numbers. And yet they're there. Everywhere we look, we find them peppered across the cosmos, like an ancient stellar confetti frozen in time. The existence of these galaxies pushes the limits of our understanding. To even detect them, astronomers have had to push technology to its extremes. The Hubble Deep Field, the Ultra Deep Field, and now the James Webb Space Telescope have peeled back layer after layer of the sky, exposing thousands of galaxies where we once saw nothing. Most of them are red, stretched by the expansion of space. But tucked into the corners are these odd, persistent blue ones, unexpectedly youthful, defiantly luminous. They're ghosts from the beginning, but their light screams with activity. And that has astronomers wondering, what forces shaped them? What dark matter halos cradled their formation? Did they merge rapidly into larger galaxies? Or were they survivors of some chaotic early era of galactic violence? To understand what these galaxies are, we need to dive into the structure of the early universe itself. After the Big Bang, the cosmos was hot, dense, and nearly uniform. But not completely. Tiny quantum fluctuations, ripples in density, were stretched to macroscopic scales by cosmic inflation. These minute variations seeded the gravitational clumps that would later collapse to form galaxies. That collapse, driven by gravity, took hundreds of millions of years to really get going. At first, the universe was filled with a fog of ionized gas, protons, electrons, and photons scattering off each other in a bright, hot plasma. This opaque era ended around 380,000 years after the Big Bang, when the universe cooled enough for neutral hydrogen to form. That allowed light to travel freely for the first time, creating what we now see as the cosmic microwave background. But galaxies didn't form instantly. For hundreds of millions of years, the universe entered what scientists poetically call the cosmic dark ages. No stars. No galaxies. Just dark matter, dark energy, and cold gas slowly gathering into invisible scaffolds. And then, something happened. Gravity did its work. The densest pockets of gas collapsed. Nuclear fusion ignited. And stars were born. The first stars, known as population 3 stars, were enormous, unstable, and short-lived. They blazed with ultraviolet light, ionizing the gas around them and triggering the era of reionization. This epoch, spanning roughly 400 million to 1 billion years after the Big Bang, saw the universe gradually lit up again. And this is where the faint blue galaxies come in. They are likely some of the first major galactic structures to emerge after reionization began. Their light, now stretched and softened by the expanding universe, tells a story of fierce activity, starbursts, mergers, rapid evolution. Some might have been the nurseries for the universe's first black holes. Others may have contributed heavily to the reionization itself, their ultraviolet radiation helping to tear apart the lingering hydrogen fog that blanketed the cosmos. But there's another mystery. The number of faint blue galaxies we observe is far greater than models predicted. It's not just that they exist, it's that there are so many of them. So either our simulations are missing some crucial element, or these galaxies hint at unknown physics in the early universe. Some theorists suggest that early star formation was more efficient than we thought. Others argue that dark matter, especially if it's warm rather than cold, might have behaved differently during those first billion years. Still others point to exotic ideas, early cosmic strings, modified gravity, even hints of interactions between dark matter and dark energy. Adding to the puzzle is the fact that many of these galaxies appear to be already mature despite their youth. Some are massive enough that they shouldn't have had time to form. Others exhibit complex structures, disks, bulges, spiral patterns, that defy expectations. It's as if evolution hit the fast-forward button. The James Webb Space Telescope, launched with the express purpose of probing the early universe, has only deepened the mystery. Its infrared instruments can pierce the dust and redshifted light better than any telescope before it. And what it sees are galaxies so old, so active, and so abundant that they challenge the timeline of cosmic evolution itself. How could such complexity arise so quickly? Are we missing an early population of hyper-efficient galaxies? Are our measurements flawed? Or are we staring at evidence that the universe is stranger than we ever imagined? As we push the boundaries of what we can observe, we also begin to question the very definition of the observable universe. Technically, it's the region from which light has had time to reach us since the Big Bang. But as space expands, regions that were once visible drift beyond reach. This creates a cosmic horizon, a boundary not of matter, but of time and causality. And these faint blue galaxies lie right at that boundary. Some may be beyond it already. The light we see from them is ancient. The galaxies themselves might no longer exist. Their stars could have burned out, collapsed into black holes, or merged into larger systems. But their light is still on its way to us, like messages from civilizations long vanished. In a way, observing these galaxies is like digging through a cosmic fossil record. Every photon is a time capsule. Every pixel in those deep field images is a portal to a forgotten age. And yet, every discovery we make seems to complicate the story rather than clarify it. We used to think the early universe was simple, a blank canvas slowly painted by gravity and time. But these galaxies hint at chaos, complexity, and perhaps even contradiction. They tell us that the universe was not just born, it exploded into form, quickly, violently, and beautifully. And they're still speaking to us. Through their faint blue light. Through the whispers at the edge of space and time. One of the most perplexing aspects of faint blue galaxies is their number. They are astonishingly numerous. Deep field surveys using Hubble and JWST reveal a universe that is far more crowded than expected. In some tiny patches of sky, smaller than a grain of sand held at arm's length, astronomers have found thousands of these galaxies. Multiply that across the entire sky, and the numbers become staggering. Billions of them, possibly trillions, each a blazing furnace of star birth from a time when the universe should have been dark and chaotic. This overwhelming abundance contradicts many of our early cosmological predictions. Originally, scientists believed that the first galaxies would be few and dim, slowly forming from the gradual coalescence of gas and dark matter. But faint blue galaxies shattered that assumption. Their presence suggests that structure in the early universe formed much more quickly, and much more efficiently, than we thought possible. This brings us to dark matter, the invisible skeleton of the cosmos. Galaxies, both ancient and modern, are believed to form inside halos of dark matter. These halos are vast, ghostly spheres made of a substance we cannot see, touch, or interact with directly. Yet without them, galaxies wouldn't exist. The gravity from dark matter clumps together gas, giving it the scaffolding it needs to collapse and ignite into stars. The faint blue galaxies at the cosmic edge may be the earliest signs of this dance between dark matter and normal matter. Their rapid star formation suggests that dark matter halos must have formed and condensed faster than previously thought, providing a nest for galaxy birth in a universe barely old enough to know what galaxies even were. But there's another twist. The light from these galaxies isn't just dim because of distance. It's dim because of expansion. As the universe stretches, so does light. A photon that started its journey as ultraviolet or visible light billions of years ago arrives on Earth as infrared. That's why the James Webb Space Telescope is such a game changer. It was built to see in infrared, giving us the clearest, most detailed views of these ancient galaxies we've ever had. And what it's showing us is both beautiful and bizarre. Some of these galaxies appear to be clumpy, chaotic, and irregular, far from the elegant spirals and structured ellipticals we see nearby. Others seem to already have surprising organization, with hints of rotation and disk-like shapes. This is another challenge to our theories. According to standard models, it should take billions of years for galaxies to settle into stable, ordered structures. So how are some of these early galaxies already showing such maturity? Could it be that galaxy evolution is far less linear than we thought? Or that we're witnessing an entirely different mode of galactic development, one that operates faster, under different physical rules? All of this raises the question of what role faint blue galaxies played in shaping the modern universe. One of the most critical epochs in cosmic history is called the era of reionization. After the Big Bang, the universe cooled and went dark. For hundreds of millions of years, there were no stars, no galaxies, just a thick fog of neutral hydrogen. But then, something changed. Light returned. The first stars and galaxies ignited, and their energy began to ionize the hydrogen around them, making the universe transparent to light for the first time since its birth. This was the reionization era, and faint blue galaxies might have been its architects. These galaxies, with their intense bursts of star formation and ultraviolet radiation, are prime candidates for reionizing the universe. But this hypothesis leads to even deeper questions. If these galaxies were responsible for reionization, how did they form so early? Where did they get the fuel? What triggered their birth in such hostile, chaotic conditions? And why did they eventually fade away? Because fade they did. Today, faint blue galaxies are incredibly rare in the local universe. The ones we see at the edge of the observable cosmos don't seem to have direct analogues nearby. That's a mystery all its own. Did they evolve into something else? Merge into larger galaxies? Or were they simply temporary features of a turbulent cosmic youth, destined to burn brightly, briefly, and then vanish? To answer that, astronomers have turned to simulations, digital universes built inside supercomputers. By modeling the laws of physics and the known ingredients of the cosmos, scientists can recreate the evolution of the universe from the Big Bang to today. These simulations, like Illustris, Eagle, and the more recent TNG-50, attempt to generate galaxies based on our understanding of how matter behaves over cosmic time. And here's where things get interesting again. For many years, these simulations struggled to produce the same number and type of faint blue galaxies that we observe. The models either created too few galaxies, or galaxies that were too red and too old. This discrepancy forced researchers to rethink their assumptions about star formation, gas cooling, supernova feedback, and dark matter behavior. In response, simulations began incorporating more complex physics, including better treatments of feedback from black holes, galactic winds, and cosmic turbulence. Only recently have some simulations begun to approach the observed number of faint blue galaxies, but the match is still imperfect. That gap between observation and theory is not a failure, it's a clue. It tells us that we still don't fully understand how galaxies form, how dark matter works, or how the early universe operated. And that's exciting, because it means the faint blue galaxies are more than just distant curiosities. They are keys to unlocking fundamental truths about reality itself. Even their faintness carries secrets. Their light is so dim that only the most sensitive instruments can detect them, and even then, we're limited. It's entirely possible, perhaps even likely, that we're only seeing a fraction of what's really out there. For every faint blue galaxy we detect, there could be dozens, hundreds, or thousands more just below the detection threshold. This is known as the missing light problem. Some astronomers believe that these undetectable galaxies could account for a significant portion of the universe's total light output during reionization, light that's simply hidden from view by current technology. And if that's true, it would mean that the early universe was even more active, more luminous, and more structured than we can currently observe. It would mean that our entire picture of cosmic history is a mere sketch, drawn from shadows. The real story is still out there, waiting for future telescopes, future physics, and future explorers to uncover it. This isn't just a technical observation, it's a cosmic clue. The fact that these galaxies appear blue despite the extreme redshift implies they were forming stars at an extraordinary pace, pumping out ultraviolet and visible light in such abundance that even after being stretched across billions of years, their brilliance remains detectable. That level of luminosity suggests that early star formation may have been more violent, more efficient, and more chaotic than models have accounted for. But that's not all. These faint blue galaxies also raise questions about the reionization era, an epoch in the universe's history that remains one of the most mysterious. After the Big Bang, the universe was a dark, opaque fog of neutral hydrogen atoms. It wasn't until hundreds of millions of years later that the first light from stars and galaxies began to pierce that fog, reionizing the hydrogen and making the universe transparent. The source of this cosmic dawn has long been debated, but many scientists now believe that faint blue galaxies were the culprits. Their intense ultraviolet radiation may have been powerful enough to tear apart the hydrogen atoms, bringing light to the darkness. If that's true, then these galaxies aren't just relics of the past, they're the very architects of the visible universe. Without them, the night sky might still be shrouded in blackness. They played a pivotal role in shaping the cosmos as we know it, and yet we've only begun to uncover their story. The James Webb Space Telescope has taken this investigation further than ever before. Its unprecedented infrared vision allows it to see deeper into the past, capturing galaxies that existed just a few 100 million years after the Big Bang. Many of them are faint, irregular, and glowing blue. These aren't elegant spirals or vast ellipticals. They're messy, compact, and turbulent. But within that chaos lies the foundation of everything. The structure of these early galaxies is another puzzle. Unlike the symmetrical disks of modern galaxies, faint blue galaxies appear clumpy and unorganized. Their stars are huddled in dense knots, their gas clouds roiling with turbulence. This irregularity makes sense in a young universe, where gravity is still sculpting the cosmic landscape. But what surprises scientists is how quickly some of these galaxies begin to show order, signs of rotation, hints of spiral arms, and the earliest signs of organized motion. It's as if the universe was in a rush, assembling galactic structures at a frantic pace, driven by forces we don't yet fully understand. Then there's the question of metallicity, the abundance of elements heavier than hydrogen and helium. In theory, the first galaxies should be composed almost entirely of primordial elements, since heavier elements are forged inside stars and distributed through supernovae. But some faint blue galaxies exhibit higher metallicity than expected. This suggests that stars were forming, dying, and enriching their surroundings at a faster rate than anticipated. It hints at a hyper-efficient stellar cycle in the early universe, one that may have accelerated chemical evolution far beyond what current models predict. And behind all of this activity lurks an even deeper mystery. Why are these galaxies so blue? Blue light is produced by hot, massive stars, the kind that burn brightly and die young. These stars don't last long, just a few million years, so any galaxy dominated by blue light must be undergoing active star formation right now, or at least at the time the light left it. But in a universe that was only a few 100 million years old, where was all this gas coming from? How were these tiny galaxies fueling such intense and sustained starbursts? Some theories suggest that gas was flowing directly into galaxies from the intergalactic medium, cold streams of pristine hydrogen funneled by dark matter filaments into gravitational wells. These cold flows could have kept the star formation fires burning, feeding the galaxies with a steady supply of raw material. If true, this would point to an elegant and efficient mechanism for early galaxy growth, one that bypasses the slower, more chaotic processes seen in later cosmic epochs. Other theories propose that mergers played a role. The early universe was a crowded place, and galaxies may have collided frequently, triggering bursts of star formation each time. These interactions could have sparked the intense blue light we now observe, transforming ordinary clouds of gas into brilliant nurseries of stars. But if mergers were the cause, then we'd expect to see more irregular shapes, more signs of disruption. And while some faint blue galaxies do appear disturbed, others seem surprisingly intact. This contradiction lies at the heart of the mystery. The more we study these galaxies, the more they resist easy categorization. They are young yet strangely evolved, chaotic yet occasionally organized, numerous yet individually distinct. Each one is a window into a different corner of the early universe, and taken together, they form a mosaic of cosmic history more intricate than we ever imagined. As we continue to collect data and refine our instruments, these faint blue galaxies promise to reveal even more. Their story isn't just about the past, it's about the present and the future of cosmology. They challenge our theories, expand our understanding, and remind us how much we still don't know. In their soft, distant glow lies the echo of creation itself, and perhaps, the answers to questions we haven't yet learned to ask. The faint blue galaxies, distant as they are, offer something more than just tantalizing glimpses of the early universe. They represent a kind of paradox, a cosmic puzzle that holds the key to understanding the formation of the first galaxies and stars. While their faintness suggests distance and their blueness hints at youth, it is their very existence that challenges our understanding of the universe's early stages. As we peer back in time, the image of the universe begins to change. These galaxies are more than just dots in the vast emptiness. They are the building blocks of the cosmos, the first major players in the shaping of the universe's large-scale structure. They are like the seeds from which everything we know today grew, each one carrying the DNA of a time before the galaxies we see today were even a thought. These galaxies are not isolated outliers, but part of a much larger cosmic tapestry. They are linked by the same fundamental processes that drive galaxy formation throughout the universe. The differences lie in the timing and the environment. The faint blue galaxies formed in an epoch of cosmic history where conditions were ideal for their explosive birth. Their story, if we could fully understand it, might give us critical insight into how other galaxies, including our own Milky Way, came to be. And what about the broader implications of these discoveries? The faint blue galaxies at the edge of the observable universe might hold the keys to unlocking a host of questions that have lingered in the minds of cosmologists and astrophysicists for years. One such question revolves around the rate of galaxy formation in the early universe. Most of the light we see from the universe today was emitted by galaxies that formed long ago. But the details of this process, how galaxies grew, when they grew, and why they grew, have remained elusive. Faint blue galaxies offer one of the clearest clues yet, showing us galaxies that were actively forming stars at a much higher rate than we see in today's universe. These early galaxies were often much smaller than the vast structures we see around us now. Despite their diminutive size, they were incredibly efficient at forming stars. This hints at an environment that was far more conducive to star formation than our current cosmic landscape. The process of galaxy formation was likely much faster back then, possibly due to the different physical conditions present in the early universe. The material in these galaxies was also far purer than what we find today. In today's galaxies, most of the gas is enriched with elements heavier than hydrogen and helium. These elements, forged in the cores of stars and distributed through supernova explosions, help form planets, life, and the intricate chemistry we see on Earth. But in these distant, blue galaxies, much of the material is still in its primordial state. They're mostly composed of hydrogen and helium, the simplest elements in the periodic table, making them more akin to the first building blocks of the universe. Understanding how stars formed in these pristine conditions could provide answers to some of the oldest questions about the origins of matter and life. However, as we study these galaxies more deeply, we begin to confront the complexities of galaxy formation. The role of dark matter, for instance, is something that continues to mystify scientists. Dark matter is thought to make up about 85% of the matter in the universe, yet we can't directly observe it. Its presence is inferred from its gravitational effects on galaxies and clusters of galaxies. The faint blue galaxies at the edge of the observable universe may give us more clues about the relationship between dark matter and galaxy formation. Did dark matter play a different role in the early universe? Or was it always the silent architect of cosmic structure? Another intriguing aspect of these galaxies is their potential to answer questions about the very nature of the universe's expansion. The fact that we can still observe these distant galaxies after all these billions of years suggests that the universe has been expanding in a very specific way. This expansion isn't uniform, it's accelerating. The discovery of the accelerated expansion of the universe, driven by what we call dark energy, has left cosmologists scrambling for explanations. But these galaxies, still visible to us after so long, might provide the observational evidence we need to better understand the effects of dark energy in the early universe. But it's not just about the distant past. The study of faint blue galaxies could help us understand the present-day cosmos as well. By learning how galaxies form and evolve over cosmic time, we can refine our models of galaxy dynamics. We can learn more about the factors that govern star formation, the behavior of interstellar gas, and the processes that lead to the growth of massive black holes at the centers of galaxies. Moreover, the discovery of these galaxies is part of a broader effort to understand how the universe began, how it grew, and what forces shaped it along the way. As we look deeper into the cosmos, we are forced to confront a humbling truth: we are still in the early stages of understanding the full scope of the universe's history. The faint blue galaxies are only one piece of the puzzle, but they are an essential one. They show us that the universe is far more complex and rich than we could have imagined, with a long and tumultuous history that is only now beginning to come into focus. In the coming decades, as technology improves and more advanced telescopes are launched, we will continue to unravel the secrets of these galaxies. We may even discover more distant galaxies, older and fainter, that push our understanding of the universe's early days even further. Perhaps we will eventually find direct evidence of the very first stars, those first flickers of light in the dark void, that signaled the dawn of the universe as we know it. The faint blue galaxies are not just relics of the past, they are beacons that point the way forward. They are our link to the universe's infancy, and they hold the potential to reveal some of the most profound mysteries of the cosmos. With each new discovery, we come closer to understanding how the universe came to be and what forces continue to shape its evolution. The story of the faint blue galaxies is far from over. In fact, it may be just the beginning of a new chapter in the history of our understanding of the cosmos. As we continue to study these galaxies, it's important to remember that they are not just distant objects. They are windows into an era that is still shrouded in mystery. These galaxies represent the early stages of galaxy evolution, offering a glimpse of a time when the universe was far younger, more chaotic, and more energetic than it is now. The implications of understanding these early galaxies are profound, not only for cosmology but also for the very nature of life itself. These faint blue galaxies are a reminder that the universe was once very different from what we see today. They embody a time when the universe was in its adolescence, with conditions that allowed for rapid star formation, chaotic mergers, and the birth of some of the earliest supermassive black holes. As we peer deeper into their history, we are not just looking at distant objects. We are looking back in time, retracing the steps of the cosmos as it grew from a hot, dense state to the vast, complex system of galaxies, stars, and planets that we observe today. There's also something inherently humbling about the scale of time involved in studying these galaxies. The light from these distant objects has traveled for billions of years to reach us, and in that time, the universe has undergone profound changes. What we see today is not what existed back then. The galaxies themselves, and the stars within them, may have long since evolved, merged, or even died. Some may have been swallowed by black holes, while others may have undergone the violent process of starburst events that saw their star-forming regions collapse in on themselves. We are seeing them as they were, not as they are now. But this sense of distance doesn't just pertain to space, it also applies to our understanding. The further we look into the past, the more difficult it becomes to interpret what we see. The universe was simpler back then, but it was also a place of raw, unstructured energy. The first stars were massive and short-lived, their death throes generating the elements that would later form the more complex galaxies, stars, and planets we know today. The faint blue galaxies that still emit this early light may hold the secrets to understanding how the first generation of stars formed and how they influenced the evolution of the cosmos. The energy released by the birth of these stars was likely immense. In fact, the intense ultraviolet radiation produced by these stars may have been responsible for reionizing the hydrogen in the early universe, an event that marked the end of the cosmic dark ages. It was during this period that the first galaxies formed, with stars beginning to light up the vast dark expanse of the universe. The faint blue galaxies we observe today may have been key players in this epochal event. their luminous glow helping to clear the fog of neutral hydrogen and ushering in a new era of cosmic exploration and evolution. Another fascinating aspect of these galaxies is their potential to offer clues about the role of supermassive black holes in the early universe. It's well known that most large galaxies contain supermassive black holes at their centers, and these black holes are thought to play a critical role in the formation and evolution of galaxies. But the relationship between black holes and galaxies in the early universe remains poorly understood. The faint blue galaxies, many of which are smaller and more irregular than the massive, well-ordered galaxies we see today, might hold the answer. Could these smaller galaxies have harbored their own supermassive black holes? And if so, how did these black holes influence their growth? The process of galaxy formation is not just about stars, it's also about gas, dust, and the dark matter that surrounds these galaxies. Dark matter, while invisible, exerts a powerful gravitational influence on visible matter, shaping the large-scale structure of the universe. Early galaxies, especially the faint blue ones, were likely embedded in massive halos of dark matter, which helped guide their growth and evolution. The relationship between dark matter and the visible matter in these early galaxies could reveal much about the fundamental forces that govern the cosmos. Furthermore, these galaxies give us an insight into the delicate balance between star formation and galaxy evolution. The intense bursts of star formation we observe in the faint blue galaxies were likely driven by the rapid accretion of gas from their surroundings, as well as the merging of smaller galaxies. This rapid star formation might have been responsible for the short lifespans of many of the stars in these galaxies. The stars that lived fast and died young left behind massive amounts of energy, potentially triggering the formation of even more stars or causing their host galaxies to collapse in on themselves. As we gather more data on these faint blue galaxies, the role of the environment in shaping them becomes increasingly important. Were these galaxies shaped by their local surroundings? Or were they influenced by broader cosmic structures, such as the vast filaments of dark matter that stretch across the universe? The environment in which a galaxy forms plays a crucial role in determining its size, shape, and behavior. By understanding the conditions that led to the formation of these faint blue galaxies, we can begin to unravel the larger processes that govern the evolution of the entire universe. Moreover, the study of these galaxies might eventually lead to breakthroughs in our understanding of dark energy, the mysterious force that is driving the accelerated expansion of the universe. Some scientists hypothesize that the expansion rate of the universe was different in the past, and by studying distant galaxies, we may be able to uncover clues about the changing nature of this expansion. If the faint blue galaxies are indeed linked to the reionization of the universe, they might also provide insights into how the expansion of the universe influenced the formation of the first galaxies and stars. In the coming years, as more sophisticated telescopes such as the James Webb Space Telescope continue to peer into the depths of space, we will undoubtedly uncover even more secrets about these faint blue galaxies. Every new discovery brings us closer to answering the fundamental questions about the early universe. What did the first galaxies look like? How did they form and evolve? And what role did they play in shaping the universe we know today? As we continue to analyze these distant, faint blue galaxies, the more we begin to realize the complexity and richness of the universe's early stages. It's no longer just about the search for the origin of galaxies, but also about how they came to be the diverse, vibrant structures that populate our night sky today. The faint blue galaxies are like time capsules, preserving clues that could unlock secrets of cosmic evolution that have been hidden for billions of years. In many ways, the study of these galaxies is like peeling back the layers of an onion, each layer revealing something more intricate, more detailed, and more fundamental about the nature of the universe. The light from these galaxies doesn't just reveal their physical makeup, it gives us a window into the conditions that existed when the universe was only a fraction of its current age. We are not simply looking at the galaxies themselves, but at the cosmic events and processes that help form them, events that occurred when the universe was still young and full of potential. Another fascinating aspect of these galaxies is their role in the larger context of the universe's overall growth and structure. These faint blue galaxies are not isolated objects, they are part of a larger cosmic network, woven into the intricate fabric of the universe. The interplay between galaxies, clusters of galaxies, and the vast voids that exist between them is a key area of research. Understanding how galaxies like these faint blue ones fit into the larger structure of the universe could provide insights into the forces that govern galaxy formation and evolution. For instance, one critical question that researchers are trying to answer is whether galaxies like these faint blue objects are simply the early building blocks of larger, more complex galaxies, or if they represent a unique phase in a galaxy's life cycle. Do these galaxies evolve into the massive elliptical galaxies that dominate the modern universe, or do they simply fade away, losing their star-forming capabilities and becoming quiet remnants of their former selves? The answer to this question may depend on a variety of factors, including the environment in which these galaxies formed and the amount of gas and dust available to fuel their growth. One theory that has gained traction in recent years is the idea of galaxy merging. This process occurs when two or more galaxies collide and merge, creating a new, often more massive galaxy. These mergers are thought to play a key role in the evolution of galaxies, particularly in the formation of large, mature systems. If these faint blue galaxies are part of a merging process, it could help explain their irregular shapes and intense star formation. The energy released during these mergers could trigger new waves of star formation, creating an environment ripe for the birth of new stars and stellar clusters. The process of galaxy merging is also tied to the presence of supermassive black holes, which lie at the center of most large galaxies. These black holes are thought to be crucial to the formation and evolution of galaxies, influencing their size, shape, and star-forming activity. In the case of the faint blue galaxies, it's possible that the gravitational forces created by merging galaxies could lead to the formation of these supermassive black holes, further fueling the growth of the galaxy as a whole. Studying the faint blue galaxies could therefore provide valuable insights into the early role of black holes in galaxy formation. However, the study of faint blue galaxies isn't without its challenges. As we mentioned earlier, these galaxies are incredibly distant, which means that the light we see from them has taken billions of years to reach us. This distance creates several hurdles for astronomers, who must rely on advanced observational techniques and powerful telescopes to peer through the vast expanse of space. The James Webb Space Telescope, with its unprecedented resolution and sensitivity, is expected to revolutionize our ability to study these galaxies in the coming years. By using infrared light, which can penetrate through cosmic dust and gas, Webb will give us a clearer view of these galaxies, allowing us to examine their structure, composition, and star formation rates with greater accuracy. In addition to these observational tools, astronomers are also turning to computer simulations to model the behavior of galaxies like these faint blue objects. By simulating the interactions between galaxies, researchers can gain a better understanding of the physical processes at work and predict how these galaxies will evolve over time. These simulations take into account factors such as gravity, gas dynamics, and star formation, allowing scientists to test different theories and hypotheses about galaxy formation and evolution. In combination with observational data, these simulations provide a powerful tool for studying the faint blue galaxies and their place in the universe. The faint blue galaxies also hold implications for our understanding of the universe's fundamental composition. As we look at these galaxies, we are not only learning about their individual characteristics, but also about the fundamental forces that govern the universe at large. For example, the study of star formation in these galaxies could provide clues about the role of dark matter, the mysterious substance that makes up a significant portion of the universe's mass. Dark matter interacts with visible matter through gravity, but it doesn't emit light, making it incredibly difficult to detect. However, its influence can be seen in the way galaxies move and interact, and by studying the distribution of dark matter in galaxies like these, we may be able to uncover new insights into this elusive substance. Similarly, the study of the gas and dust that surround these galaxies could reveal information about the nature of dark energy, the mysterious force that is causing the accelerated expansion of the universe. Some scientists believe that dark energy could be responsible for the strange behavior of distant galaxies, causing them to appear more stretched out or disorganized than expected. By studying how these faint blue galaxies interact with their environment, we may gain a better understanding of the larger forces at play in the universe's evolution. The faint blue galaxies are not just objects of academic curiosity. They are a testament to the richness and complexity of the cosmos. As we continue to study them, we are not only uncovering the secrets of their own evolution, but also gaining insights into the larger story of the universe. In doing so, we are drawing closer to answering some of the most profound questions in science. How did the universe come to be? How did galaxies form, and how have they evolved over time? And what does the future hold for the galaxies we see today? These questions may take centuries, even millennia, to fully answer. But with each discovery, we are one step closer to understanding our place in the vast expanse of space and time. The faint blue galaxies at the edge of the observable universe are not just distant objects. They are the key to unlocking the mysteries of the cosmos. And as we continue to peer deeper into the universe, we are bound to uncover even more astonishing secrets that will reshape our understanding of everything we know about the universe and our place within it. As we venture further into the mysteries surrounding the faint blue galaxies, it's essential to consider the broader implications of our discoveries. These galaxies, while incredibly distant and faint, are part of a larger cosmic structure that spans the entirety of the observable universe. They are not isolated objects, but rather, they are woven into the intricate tapestry of cosmic history. Their study offers us more than just an understanding of the past. It provides us with a glimpse of the future. One of the most compelling aspects of these faint blue galaxies is their relationship with the large-scale structure of the universe. Galaxies are not evenly distributed across space. Instead, they are arranged in vast, interconnected clusters and superclusters, with enormous voids in between. The faint blue galaxies at the edge of the observable universe are situated at the farthest reaches of these structures, where the expansion of the universe is most apparent. Studying these galaxies gives us insight into the dynamics of cosmic expansion and the way in which matter and energy are distributed across the universe. The expansion of the universe, a process that began with the Big Bang, is not uniform. It is influenced by the presence of matter, energy, and the mysterious forces that govern the universe's evolution, including dark energy and dark matter. The faint blue galaxies, by virtue of their position at the edge of the observable universe, offer us a unique perspective on this expansion. They represent a snapshot of the universe as it was billions of years ago, just as it was beginning to take shape. This relationship between the galaxies and the expanding universe raises intriguing questions about the ultimate fate of these objects. Will they continue to drift apart as the universe expands, or will they eventually be pulled together by the forces of gravity? Some scientists believe that, over vast timescales, the expansion of the universe will slow down, and galaxies will begin to move closer together once again. This process, known as the Big Crunch, could potentially lead to the formation of new, even more massive galaxies. Other theories suggest that the expansion will continue indefinitely, causing galaxies to become increasingly isolated and distant from one another. The fate of the faint blue galaxies is tied to these larger cosmic questions, and understanding their evolution may provide crucial clues to the universe's long-term destiny. In addition to the larger cosmic implications, the study of faint blue galaxies also holds significant potential for advancing our understanding of fundamental physics. The light emitted by these galaxies provides us with a direct window into the behavior of matter and energy in the early universe. As we examine the properties of this light, we are able to test the predictions of various cosmological models, including those related to the formation of galaxies, the behavior of dark matter, and the nature of dark energy. By comparing the observed properties of faint blue galaxies with theoretical models, we can refine our understanding of the fundamental forces that shape the universe. One particularly intriguing aspect of these galaxies is the way in which they challenge our current understanding of galaxy formation. The faint blue galaxies appear to be undergoing rapid star formation, which is unusual for galaxies at such great distances. In most cases, galaxies that are this far away are thought to be in a more mature state, having already completed most of their star-forming activity. The fact that these galaxies are still actively forming stars suggests that they are in an earlier phase of their evolution, potentially offering us a glimpse into the conditions that existed in the very early universe. This has profound implications for our understanding of how galaxies form and evolve. It suggests that the processes responsible for galaxy formation were more complex and dynamic than previously thought. Rather than following a simple, linear path of growth, galaxies may experience bursts of star formation at various stages in their evolution, with external factors such as gravitational interactions and the availability of gas playing a key role in shaping their development. As we look at the faint blue galaxies, we are also confronted with the question of their ultimate fate. Will they continue to grow and evolve into the massive galaxies we see in the nearby universe? Or will they remain small, isolated objects, unable to fully mature? The answer to this question may depend on a variety of factors, including their proximity to other galaxies and the availability of resources. It's possible that these galaxies will eventually merge with larger galaxies, triggering new waves of star formation and altering their overall structure. Alternatively, they may gradually fade away, their star formations slowing as they run out of the gas needed to fuel new stars. One thing is certain, the study of faint blue galaxies is far from over. As our observational capabilities continue to improve, we will be able to study these distant objects in even greater detail. New telescopes and instruments, such as the James Webb Space Telescope and future ground-based observatories, will provide us with unprecedented views of the distant universe, allowing us to peer into the heart of these galaxies and unlock their many secrets. With each new discovery, we will come closer to understanding not just the faint blue galaxies themselves, but also the broader processes that have shaped the universe we see today. The ongoing research into these galaxies also has significant implications for our understanding of the origins of life. By studying the conditions in these early galaxies, scientists are gaining insights into the environments that may have been present when the first stars and planets were forming. This, in turn, could help us better understand the conditions required for life to emerge elsewhere in the universe. Are the environments of these faint blue galaxies similar to those that gave rise to life on Earth? Could life have formed in other parts of the universe under similar conditions? These are the types of questions that could be answered through continued study of these distant galaxies. Another fascinating aspect of the study of faint blue galaxies is their potential role in the cosmic web. The cosmic web is a vast, interconnected network of galaxies, clusters of galaxies, and dark matter that spans the entire universe. Faint blue galaxies, like other galaxies, are part of this web, and their interactions with the surrounding cosmic structures could play a significant role in shaping their evolution. For instance, the gravitational pull of nearby galaxies or the distribution of dark matter could influence the rate of star formation in these galaxies, as well as their overall growth and development. As we continue to explore the faint blue galaxies at the edge of the observable universe, we are not only uncovering the mysteries of the past, but we are also laying the groundwork for future discoveries. Each new piece of information adds to our growing understanding of the universe, bringing us closer to answering some of the most profound questions in science. What is the true nature of dark matter and dark energy? How do galaxies form, and how do they evolve over time? What is the fate of the universe, and how does it relate to the distant galaxies that populate its vast expanse? These questions are at the heart of modern cosmology, and the study of faint blue galaxies offers us one of the best opportunities to address them. Through continued research and observation, we are getting closer to unlocking the secrets of the universe, one galaxy at a time. As we continue to uncover more about the faint blue galaxies at the edge of the observable universe, we encounter an even greater mystery: the role these galaxies play in the larger cosmic narrative. Their faint light, a beacon from an era long past, is more than just a distant point in the sky. It's a fragment of the universe's early history, carrying with it clues that could help us piece together the most fundamental aspects of our existence. One of the key aspects of these galaxies is their role in the process of reionization, a critical event in the early universe. Reionization refers to the period when the universe, which had been dark and opaque following the Big Bang, began to clear up as the first stars and galaxies formed. This event occurred roughly 1 billion years after the Big Bang and marks a crucial phase in the evolution of the cosmos. The faint blue galaxies, with their ongoing star formation, are prime candidates for shedding light on this process. The light emitted by these early stars ionized the hydrogen gas that filled the universe, transforming it from a neutral state into an ionized one. This was a pivotal moment in the history of the universe, as it allowed light to travel freely through space, marking the transition from an opaque cosmos to a transparent one. Understanding how this process unfolded and the role that galaxies like the faint blue ones played in it is crucial for understanding the larger evolutionary timeline of the universe. These galaxies, located at the edge of the observable universe, offer us a glimpse into the universe as it was during this critical period. As we study their light, we can begin to piece together the timeline of reionization and the conditions that led to the formation of the first stars and galaxies. By understanding this process in greater detail, we can also learn more about the nature of the early universe, how it was structured, how it evolved, and how the first building blocks of matter came together to form the galaxies, stars, and planets that populate the cosmos today. Another fascinating aspect of these galaxies is their potential connection to the dark ages of the universe. Before the first stars formed, the universe was in a state known as the cosmic dark ages. During this time, the universe was filled with hydrogen and helium gas, and no light had yet been emitted by stars. This period is one of the least understood phases of cosmic history, as it occurred before the first galaxies began to form. The faint blue galaxies, by providing us with a snapshot of the early universe, may offer crucial information about the transition from the dark ages to the era of reionization. As we look at the faint blue galaxies, we are not only observing distant objects in space, but we are also witnessing a critical chapter in the history of the universe. These galaxies are like time capsules, preserving information about the universe's infancy. Their study allows us to probe deeper into the earliest epochs of cosmic history, helping to bridge the gap between the Big Bang and the formation of the first complex structures in the universe. The implications of studying these galaxies extend far beyond understanding the past. They also have profound implications for our understanding of the future of the universe. The fate of these distant galaxies is tied to the ongoing expansion of the universe. As the universe continues to expand, these galaxies will become increasingly isolated, moving farther away from each other. The current rate of expansion suggests that these galaxies will eventually be too distant for us to study in any meaningful way. However, it is possible that some of these galaxies will eventually collide with one another, leading to the formation of larger, more massive galaxies. This process, known as galaxy merging, is a common event in the universe. When galaxies collide, their stars, gas, and dust interact, often triggering new waves of star formation. These interactions can lead to the growth of supermassive black holes at the centers of galaxies and can even lead to the creation of new structures, such as star clusters and planetary systems. The role of these faint blue galaxies in this process is still a topic of active research. While many of these galaxies are thought to be relatively isolated, they may eventually be drawn together by the forces of gravity, forming larger galactic structures. In this way, the faint blue galaxies could play a key role in the future evolution of the universe, contributing to the formation of new galaxies and helping to shape the cosmic landscape in the billions of years to come. Beyond the realm of galactic evolution, the study of faint blue galaxies also has important implications for our understanding of the fundamental forces that govern the universe. These galaxies, like all other objects in the universe, are subject to the laws of physics, but the extreme distances and conditions under which they exist make them an ideal testbed for studying the nature of these forces. For example, one of the most significant challenges in modern cosmology is understanding the nature of dark matter and dark energy. These mysterious substances make up the vast majority of the universe's mass and energy, yet they remain elusive and difficult to detect. The faint blue galaxies, because of their location at the edge of the observable universe, are particularly valuable in this regard. They are influenced by the gravitational pull of dark matter and are likely affected by the mysterious forces of dark energy. By studying these galaxies, we can learn more about the nature of these substances and how they influence the behavior of galaxies and other cosmic structures. Additionally, the study of these galaxies offers valuable insights into the behavior of light and the nature of the space-time fabric itself. The light emitted by these galaxies has traveled billions of years to reach us, passing through vast stretches of space and being influenced by the expansion of the universe. This light provides a unique opportunity to test our understanding of relativity and the way in which the fabric of spacetime behaves over vast distances. As we continue to explore the faint blue galaxies, we are confronted with even more questions. How do the environments of these galaxies compare to those of galaxies closer to home? What role does the surrounding cosmic environment play in shaping their development? What are the unique properties of the stars in these galaxies, and how do they differ from stars in nearby galaxies? By studying these galaxies in greater detail, we can answer these questions and more, shedding light on the many mysteries that remain in the universe. One of the most fascinating aspects of these galaxies is their potential to reveal new aspects of the physics of star formation. The faint blue galaxies are actively forming stars, and their star formation processes may differ from those in more mature galaxies. By studying these galaxies, we can gain a better understanding of the conditions that lead to the birth of stars and how the interplay between gas, dust, and gravity leads to the formation of new stars. This knowledge is essential for understanding the overall process of galaxy evolution and the ways in which galaxies grow and change over time. As the study of faint blue galaxies progresses, we will continue to refine our understanding of the universe and its many mysteries. With the advent of new observational tools and advanced telescopes, such as the James Webb Space Telescope, we will be able to peer even deeper into the cosmos and uncover even more secrets about these distant, faint objects. Every new discovery brings us closer to answering the fundamental questions about the nature of the universe and our place within it. Ultimately, the study of faint blue galaxies at the edge of the observable universe is not just about understanding the past or the present, it's about understanding the very nature of the universe itself. These galaxies are windows into the earliest epochs of the cosmos, and through them, we can learn about the forces and processes that have shaped the universe over billions of years. As we continue to explore the faint blue galaxies, we unlock the secrets of the universe's origins, its evolution, and its future. As we look deeper into the faint blue galaxies at the edge of the observable universe, we realize that their study might not only answer questions about the early cosmos but also open entirely new avenues of inquiry. These galaxies, whose faint light has traveled across unimaginable distances and time, offer us a unique glimpse into an era when the universe was still in its infancy. They are like fossilized remnants of a distant past, holding within them clues about the formation of stars, galaxies, and the very fabric of spacetime. One of the most intriguing aspects of these galaxies is their role in the broader cosmic architecture. Understanding the evolution of these faint blue galaxies is crucial because they may represent a stage of galactic development that we have not yet fully witnessed in our more nearby, mature galaxies. These galaxies are thought to be relatively young in cosmic terms, and their star formation is still vigorous. This contrasts with more evolved galaxies, which may have already exhausted much of their star-forming material. These early galaxies may be in a kind of stellar adolescence, a phase where the process of star formation is in full swing. They are like cosmic laboratories, providing scientists with an opportunity to study how galaxies like our Milky Way may have evolved. By studying the star formation rates, the types of stars that dominate these galaxies, and the processes driving their evolution, we can gain insights into the early stages of galactic life. This, in turn, helps us piece together the larger puzzle of how galaxies form, grow, and eventually fade. At the same time, these galaxies challenge our understanding of how large-scale structures in the universe come into being. Galaxies do not exist in isolation. They are part of a complex web of cosmic structures, from clusters to superclusters, all interconnected by the forces of gravity. The faint blue galaxies may hold the key to understanding how galaxies first began to cluster together, how cosmic filaments formed, and how the large-scale structure of the universe came into existence. As we observe these galaxies, we are not just studying isolated objects, we are gaining insights into the cosmic tapestry itself. There is also the question of whether these faint blue galaxies could be remnants of a primordial time, untouched by the various processes that have shaped other galaxies. While some scientists believe that these galaxies are relatively young and still in the process of evolving, others have suggested that they could be the fossils of the early universe, providing a direct link to a time when the cosmos was a much simpler place. If this theory holds, these galaxies might be among the closest things we have to a window into the universe's earliest stages, before the more complex processes of galaxy formation and evolution began. One of the most exciting possibilities is that these faint blue galaxies could provide the missing link between the cosmic dark ages and the era of galaxy formation. If they are indeed remnants of the earliest cosmic structures, they may offer direct evidence of the first galaxies and their formation. Studying their chemical compositions, star populations, and overall structures could allow us to trace the origins of galaxies in unprecedented detail. In addition to their importance for understanding galaxy formation, these galaxies could also help us unravel the mysteries of dark matter and dark energy. These two elusive forces are believed to make up most of the universe's mass and energy, yet they remain largely undetectable. The faint blue galaxies, by virtue of their extreme distances, are influenced by the effects of dark matter and dark energy more than galaxies closer to us. Their study could provide critical clues about the nature of these mysterious components and their role in shaping the evolution of the universe. Moreover, these galaxies are located at such vast distances that their light provides an invaluable opportunity to study the effects of cosmic expansion. As light travels across the universe, it is stretched by the expansion of space, a phenomenon known as redshift. The farther away an object is, the more its light is redshifted. This allows astronomers to measure how fast the universe is expanding at various points in time, helping to refine our understanding of the expansion rate and the overall dynamics of the universe. Interestingly, the study of these galaxies also has implications for the larger field of cosmology. As we observe these distant objects, we are not just looking at them in isolation. We are examining them within the context of the evolving universe. The faint blue galaxies offer us a snapshot of the universe at a time when the first stars and galaxies were forming, providing a key piece in the puzzle of cosmic history. This is where cosmology and astronomy intersect, as understanding the history and structure of the universe depends on these kinds of observations. But beyond their scientific significance, these galaxies also tap into something more fundamental: our curiosity about the cosmos. They embody the human desire to understand our origins and our place in the universe. As we peer into the distant reaches of space, we are not just uncovering facts about the universe's past. We are confronting the profound mystery of how everything came to be. Why does the universe exist? How did it evolve? Are we alone in this vast, unfathomable expanse of space? These questions, which have intrigued humanity for millennia, are reflected in the study of galaxies at the edge of the observable universe. As we continue to explore these faint blue galaxies, one thing is clear: they are more than just distant objects in the night sky. They are critical pieces of the cosmic puzzle, offering us glimpses into a past that can help us understand the present and, perhaps, the future of the universe. Every new discovery made about these galaxies brings us closer to answering some of the most profound questions in science. Yet, even as we learn more about these distant objects, we must also acknowledge the limits of our current understanding. The farther we look into the universe, the more we encounter new mysteries. Each new discovery raises new questions, and the answers to these questions may lead us down entirely new paths of inquiry. The faint blue galaxies are just one example of this ongoing process of discovery, a process that has only just begun. In the future, as our technology advances, we will be able to observe these galaxies with even greater detail. With instruments like the James Webb Space Telescope, which is specifically designed to study the distant universe in unprecedented detail, we may soon be able to observe these faint blue galaxies with a level of precision that was previously unimaginable. This could lead to groundbreaking discoveries about the nature of star formation, the role of dark matter and dark energy, and the evolution of galaxies over time. The faint blue galaxies at the edge of the observable universe are more than just distant objects in the cosmos. They are a window into the early universe, offering clues about the formation of stars and galaxies, the process of reionization, and the fundamental forces that shape the universe. Their study is not just about understanding the past. It is about unraveling the mysteries of the cosmos and our place within it. As we continue to explore these galaxies, we are not only deepening our knowledge of the universe but also expanding our understanding of the very nature of existence itself. As we continue our journey into the faint blue galaxies at the edge of the observable universe, we must pause to reflect on the significance of what we are witnessing. The deeper we peer into the vastness of space, the more we realize how much of the universe remains shrouded in mystery. These faint blue galaxies, stretching across the fabric of space-time, act as messengers from the past, and their light provides us with rare insights into an era long gone. Yet, despite our growing understanding, each discovery raises new questions, many of which may challenge the very foundations of modern cosmology. At the core of our exploration is the question of what these galaxies can tell us about the early universe's conditions. The faint blue hue of these galaxies is not an arbitrary feature. It is a direct result of the composition of the stars that reside within them, particularly the high rate of star formation. These galaxies are often dominated by young, hot, and blue stars. Blue light, in particular, is associated with hotter, younger stars that burn through their fuel at an accelerated pace, releasing massive amounts of energy in the process. This characteristic makes them stand out from the older, redder galaxies that have moved past their peak star-forming years. Observing these galaxies allows astronomers to study how star formation works in its earliest stages, and by extension, how galaxies themselves evolve. These faint blue galaxies could hold the keys to understanding the processes that led to the formation of the first stars. This critical event, often referred to as the Epoch of Reionization, occurred roughly 1 billion years after the Big Bang, marking the end of the cosmic dark ages. During this time, the universe underwent a dramatic transformation as the first generation of stars began to light up the darkness, ionizing the surrounding hydrogen gas and allowing light to travel freely through space for the first time. The light from these faint blue galaxies, which is among the oldest light we can observe, provides us with a window into this pivotal moment in the universe's history. But the story doesn't end there. The faint blue galaxies also offer us clues about the environment in which these stars formed. One of the key questions scientists have is how the chemical makeup of the early universe allowed stars to form in the first place. In the aftermath of the Big Bang, the universe was primarily composed of hydrogen and helium, with trace amounts of lithium. As stars began to form, they fused these elements to create heavier elements, a process known as nucleosynthesis. The presence of these heavier elements in a galaxy's stars and gas clouds can tell astronomers how much time has passed since the Big Bang and what kinds of processes were at work in the early universe. This is where the study of metallicity, an important property of a galaxy, comes into play. Metallicity refers to the abundance of elements heavier than hydrogen and helium within a star or galaxy. Younger galaxies, like the faint blue ones, tend to have lower metallicities compared to older galaxies. This lower metallicity is a hallmark of early universe star formation, where fewer heavy elements were available to build stars. As we study the metallicity of these faint blue galaxies, we can gain insights into the chemical evolution of the cosmos and how elements like carbon, oxygen, and nitrogen, key ingredients for life, were first produced. Another crucial aspect of these galaxies is the rate of star formation occurring within them. The fact that these galaxies appear blue is a sign of active star formation, but how exactly does this process unfold at the extreme distances we are observing? By studying the characteristics of star formation in these galaxies, we can learn about the factors that influence the birth of stars on a galactic scale. Is the process primarily driven by the availability of gas, or are there other factors, like the presence of dark matter, which remains an enigma in many respects, that play a larger role? The ongoing study of faint blue galaxies is helping scientists refine their understanding of these complex processes and their relationship to the evolution of the cosmos. One of the most captivating features of these distant galaxies is their role in shaping our understanding of the cosmic web. The cosmic web is the vast, interconnected structure that permeates the universe, composed of galaxy clusters, superclusters, and vast voids. These galaxies, often residing at the edges of the observable universe, help to paint a picture of how the web began to take shape in the very early stages of cosmic history. As galaxies formed and began to cluster together under the influence of gravity, they began to trace out the filaments and nodes of this massive cosmic structure. Studying the position and distribution of these galaxies in the context of the cosmic web could reveal how the universe evolved from a uniform, nearly featureless expanse into the complex and highly structured universe we observe today. In addition to the structural role that these galaxies play, there is the question of their internal dynamics. How do galaxies this far from the center of the universe remain so actively involved in star formation? Are there processes at work that are distinct from what we observe in closer, more evolved galaxies? The study of their rotation curves, how galaxies spin, can provide key insights into the distribution of matter within these galaxies. The rate at which these galaxies rotate could help us understand the role of dark matter in their formation and evolution. But perhaps one of the most profound implications of studying these faint blue galaxies is their potential to challenge our understanding of the nature of time and space itself. When we look at these galaxies, we are not merely looking at distant objects, we are looking back in time. The light from these galaxies has taken billions of years to reach us, meaning we are observing them as they were in the distant past. This means that these galaxies have already evolved, and some may have changed in ways that are impossible for us to detect. Some of the galaxies we see today may have already merged with other galaxies, or their star formation may have slowed down or ceased entirely. The study of faint blue galaxies at the edge of the observable universe also raises important philosophical and scientific questions. If we can observe these distant galaxies, what does that say about the limits of the observable universe? Does the observable universe represent the ultimate boundary of what we can know, or is it simply a reflection of the limitations of our current technology? As we develop more advanced telescopes and instruments, our ability to observe even farther will continue to push these boundaries. The notion that the universe might have no true edge, but instead stretches beyond what we can observe, challenges our understanding of spacetime itself. Additionally, there is the issue of dark energy, the mysterious force that seems to be accelerating the expansion of the universe. These faint blue galaxies, by virtue of their distance from us, are being influenced by the effects of dark energy in ways that are not fully understood. Some scientists speculate that these galaxies, being located at the outermost edges of the observable universe, may be some of the first places where the influence of dark energy is felt most acutely. By studying the properties of these galaxies, we could gain valuable insights into how dark energy operates and how it might continue to shape the evolution of the universe in the future. As we stand on the threshold of new discoveries, we can't help but marvel at the extraordinary nature of these faint blue galaxies. In their distant light, we glimpse the earliest stages of galaxy formation, the birth of stars, and the intricate dance of cosmic forces that shape the universe we now inhabit. Each observation, each discovery, brings us closer to understanding the complex and beautiful structure of the cosmos. The role of these galaxies in our broader understanding of the universe cannot be overstated. They are not just distant, faint objects in the night sky, they are vital pieces of the cosmic puzzle. As we continue to push the boundaries of our knowledge and technology, these galaxies will remain crucial in our quest to understand the origins, evolution, and ultimate fate of the universe itself. As we continue to delve deeper into the mysteries of the faint blue galaxies scattered across the edges of the observable universe, we uncover even more fascinating aspects of these distant cosmic objects. Beyond their role in star formation, these galaxies are providing scientists with insights into the nature of the early universe, the formation of structure on a cosmic scale, and the complex interplay of forces that govern the evolution of galaxies over billions of years. These seemingly distant and elusive objects are, in fact, key to unlocking some of the universe's greatest secrets. One of the primary ways in which these galaxies shed light on the early universe is through their gas content. Gas is the fundamental ingredient for star formation, and studying the gas in these distant galaxies can provide clues about the processes that govern the birth of stars in the very early stages of the universe. The gas within these faint blue galaxies is often seen as a reservoir for new stars, and its properties can reveal a great deal about the conditions that existed when the universe was still in its infancy. One of the most intriguing aspects of the gas in these galaxies is its chemical composition. As we mentioned earlier, the first stars were composed primarily of hydrogen and helium, with trace amounts of other elements like lithium. Over time, As stars formed and died, they began to fuse hydrogen and helium into heavier elements, a process known as nucleosynthesis. These heavier elements, known as metals in astronomical terms, are essential for the formation of planets and life as we know it. The faint blue galaxies we observe today often have relatively low metallicity, indicating that they are relatively young and still in the process of forming stars. By studying the gas in these galaxies, scientists can trace the chemical evolution of the universe and learn how elements like oxygen, carbon, and nitrogen, critical building blocks for life, were first created. Furthermore, the presence of ionized gas in these galaxies can reveal valuable information about the conditions under which stars are forming. The gas surrounding young stars tends to become ionized by the intense radiation emitted by these hot, energetic stars. This ionized gas forms nebulae, vast, glowing clouds of gas that are often seen in regions of intense star formation. The study of these ionized nebulae can provide crucial insights into the physical processes at work in these galaxies, such as the rate of star formation, the amount of energy being released by young stars, and the way that gas is being processed within the galaxy. The more we learn about the ionized gas in these galaxies, the better we can understand how star formation proceeds in the early universe and how galaxies evolve over time. While gas and star formation are important aspects of these galaxies, the role of dark matter cannot be overlooked. Dark matter, the invisible substance that makes up a large portion of the universe's mass, has a profound impact on the formation and evolution of galaxies. It is believed that dark matter acts as a kind of cosmic scaffold, providing the gravitational pull necessary to gather gas and dust, which then condense into stars and galaxies. Without dark matter, galaxies would not form in the way we observe them today. The faint blue galaxies at the edges of the observable universe provide an ideal testing ground for studying the effects of dark matter. These distant galaxies are not only some of the youngest and least evolved galaxies in the universe, but they also reside in regions of space where the influence of dark matter is still being felt most strongly. By studying the distribution of stars and gas in these galaxies, scientists can infer the presence and distribution of dark matter, which remains one of the most enigmatic and poorly understood components of the universe. Understanding how dark matter shapes the formation of galaxies in the distant past can provide important clues about its role in the universe's evolution and its ultimate fate. Another fascinating aspect of these faint blue galaxies is their relationship to the larger-scale structure of the universe. Galaxies do not exist in isolation. They are part of a vast, interconnected cosmic web of galaxies, clusters, and superclusters. The cosmic web is one of the most striking features of the universe, and its formation is intricately tied to the processes that govern galaxy formation and evolution. These faint blue galaxies, located on the periphery of the observable universe, provide us with a glimpse into the early stages of this cosmic web. The galaxies that populate the cosmic web are not distributed evenly throughout space. Instead, they tend to cluster together in large groups, forming long, thread-like structures that stretch across vast distances. These structures are the result of the gravitational forces acting on galaxies over billions of years. As galaxies fall into these clusters, they become intertwined with one another, their motions influenced by the gravity of the other galaxies around them. The faint blue galaxies at the edges of the universe are often found in regions of space where the cosmic web is just beginning to take shape. Studying their distribution can help astronomers understand how the larger-scale structure of the universe formed and how galaxies were drawn together into these massive clusters over time. As we examine these galaxies, we must also consider their relationship to the larger processes that govern the universe's fate. The study of distant galaxies is intrinsically linked to the concept of cosmic evolution, how the universe changes over time. These faint blue galaxies are some of the most ancient objects we can observe, yet they are also in a state of constant change. Over billions of years, they will evolve into more mature galaxies, eventually transforming into the older, redder galaxies that dominate the universe today. This process of galaxy evolution is still not fully understood, but by studying galaxies like these, we can begin to piece together the puzzle of how galaxies change over time and what factors drive this transformation. In addition to their role in understanding galaxy formation and evolution, these faint blue galaxies may also hold the key to understanding the ultimate fate of the universe. One of the most exciting and speculative areas of research in cosmology is the study of the expansion of the universe and its eventual fate. Current observations suggest that the universe is expanding at an accelerating rate, a phenomenon attributed to the mysterious force known as dark energy. The faint blue galaxies, located at the farthest reaches of the observable universe, are being stretched apart by the expansion of space-time. By studying how these galaxies are moving, scientists can gain valuable insights into the nature of dark energy and how it is affecting the universe's expansion. The faint blue galaxies at the edges of the observable universe also raise profound questions about the nature of space and time. As we look deeper into space, we are essentially looking back in time, observing these galaxies as they were billions of years ago. This concept of looking back in time is one of the most fascinating aspects of modern cosmology. These galaxies allow us to peer into the distant past, witnessing the universe as it was in its infancy. But they also force us to confront the limits of our understanding of time and space. If the universe is constantly expanding, what does that mean for our perception of time itself? Can we ever truly understand the beginning of the universe, or is our understanding forever limited by the nature of light and time? As we stand on the precipice of new discoveries, one thing is certain: the faint blue galaxies at the edge of the observable universe are not merely distant, obscure objects. They are windows into the past, offering us a glimpse into a time when the universe was young and full of potential. Every new discovery about these galaxies brings us one step closer to understanding the fundamental forces that shape the universe, and in doing so, it helps us answer some of the most profound questions about our existence and our place in the cosmos. As we continue to explore the faint blue galaxies at the edges of the observable universe, we enter into a realm where cosmic mysteries deepen, and the boundaries of human knowledge are constantly challenged. Each new discovery brings us closer to understanding not only the formation of galaxies but the broader mechanisms that govern the universe itself. As these galaxies continue to intrigue scientists, one of the primary questions that emerge revolves around the very nature of their light. Light, as we experience it, is not just a simple wave traveling through space. It is a messenger carrying crucial information about the source from which it emanates. In the case of the faint blue galaxies, the light we observe today is the result of a complex interplay of various factors, including the age of the galaxy, the composition of its stars, and the distance it has traveled across the cosmos. The color of these galaxies, often blue, reveals to us important details about their star formation activity and the age of the stars within them. The blue hue of these galaxies suggests that they are in a state of rapid star formation. Young, hot stars emit higher energy blue light, while older stars emit redder light. Therefore, the blue appearance of these galaxies is a key indicator that they are still in the process of forming new stars, and that their stellar population is relatively young. This contrasts sharply with older galaxies, which tend to appear redder due to the aging of their stars and the cessation of new star formation. By examining the light from these faint blue galaxies, astronomers can gain valuable insight into the rate of star formation in the early universe, as well as the conditions that allowed for such active processes to occur. One of the most fascinating aspects of observing the light from these distant galaxies is the effect of redshift. As light travels across vast distances, the expansion of the universe stretches the wavelength of the light, causing it to shift toward the red end of the spectrum. This phenomenon is known as redshift, and it is one of the key tools astronomers use to measure the distance to distant galaxies. The more redshifted the light is, the farther away the galaxy is from us, and the earlier in the universe's history it existed when the light was emitted. For faint blue galaxies at the edge of the observable universe, the redshift is often so extreme that their light is stretched to the point where it appears far redder than when it was initially emitted. This stretching of light allows astronomers to study these galaxies as they existed billions of years ago, providing a glimpse into a time when the universe was much younger and more energetic. As a result, these galaxies are invaluable tools for understanding the evolution of the universe, as they allow scientists to trace the history of cosmic events over vast stretches of time. The concept of redshift is intrinsically tied to our understanding of the universe's expansion. Since the time of the Big Bang, the universe has been expanding, causing galaxies to move away from each other. This expansion, which continues to this day, stretches the fabric of space itself. It is not just galaxies moving through space, it is space itself that is expanding, carrying galaxies with it. The greater the distance to a galaxy, the faster it appears to be moving away from us, a phenomenon known as the Hubble flow. By studying the redshift of light from these distant galaxies, we can measure the rate of expansion and refine our models of the universe's growth over time. The light from these faint blue galaxies also plays a crucial role in helping us understand the larger-scale structure of the universe. These galaxies are not isolated points in space. They are part of a vast, interconnected cosmic web that stretches across the entire universe. The study of galaxies at the edges of the observable universe helps us trace the formation and evolution of this web, shedding light on how galaxies have clustered together over billions of years and how the cosmic web itself has evolved. In this context, the faint blue galaxies provide important clues about the role of dark energy in the expansion of the universe. Dark energy, which makes up roughly 70% of the universe's total energy content, is responsible for the accelerated expansion of the universe. By studying how galaxies at the edge of the observable universe are behaving, scientists can begin to understand how dark energy influences the structure and dynamics of the cosmos on the largest scales. This understanding may eventually help us uncover the true nature of dark energy, which remains one of the greatest mysteries in modern cosmology. One of the most compelling aspects of these faint blue galaxies is that they offer us a window into the earliest stages of galaxy formation. While many of the galaxies we observe today have undergone billions of years of evolution, the faint blue galaxies at the edges of the observable universe are some of the youngest galaxies we can study. They are often in a state of rapid star formation, with new stars being born at an extraordinary rate. This active star formation is crucial for understanding how galaxies like our own Milky Way came into being, as it represents the early stages of the processes that ultimately led to the formation of mature galaxies. These galaxies are also revealing new insights into the role of gas in galaxy evolution. The gas in these distant galaxies plays a critical role in the formation of new stars, and the composition of this gas provides important clues about the conditions that existed in the early universe. As we study the gas in these galaxies, we can gain a better understanding of how the first generations of stars were formed, and how the gas in these galaxies has evolved over time. This gas is often rich in hydrogen and helium, the two most abundant elements in the universe, but over time, as stars form and die, heavier elements are produced through nucleosynthesis. By studying the chemical composition of the gas in these galaxies, we can trace the chemical evolution of the universe and learn more about how elements like carbon, oxygen, and nitrogen were first created. While these faint blue galaxies provide valuable insights into the early universe, they also challenge our current understanding of cosmology. For example, the high rate of star formation in these galaxies suggests that the processes governing star formation in the early universe may have been more efficient than previously thought. This could imply that galaxies in the early universe formed much more quickly than we had assumed, which in turn could alter our models of galaxy formation and evolution. Additionally, the presence of these galaxies at the farthest reaches of the observable universe raises questions about the nature of the universe's expansion and the limits of our observational capabilities. As we continue to observe and study these distant galaxies, we are confronted with the possibility that there may be even more faint, blue galaxies out there, beyond the limits of our current observational techniques. Our ability to detect these galaxies is constrained by the sensitivity of our telescopes, and the sheer distance that separates us from these distant objects. As technology advances, it is likely that we will be able to peer even further into the universe's past and uncover even more galaxies that have never before been seen by human eyes. The faint blue galaxies at the edge of the observable universe are not just distant, faint points of light. They are windows into the universe's past, offering us a glimpse into a time when the cosmos was young and full of potential. These galaxies are the key to understanding the fundamental processes that have shaped the universe, from the formation of the first stars to the evolution of the cosmic web. As we continue to explore these distant realms, we are reminded of just how much there is still to discover about the universe and our place within it. The study of these galaxies is far from over, and as new techniques and technologies emerge, we will undoubtedly continue to uncover new mysteries and gain deeper insights into the universe's vast, intricate history. The faint blue galaxies are more than just objects of scientific curiosity. They are the building blocks of our understanding of the cosmos, and they hold the key to unlocking some of the most profound questions in modern science. As we venture deeper into the study of faint blue galaxies, we uncover not only the fundamental processes that govern the formation and evolution of galaxies but also the broader implications of how the universe itself came into being and how it will continue to evolve. The faint blue galaxies we observe at the edge of the observable universe are like snapshots of a distant past, snapshots that show us the universe in its infancy, still in the throes of cosmic adolescence. Their light, having traveled across billions of years, contains invaluable information about the early universe that we are only beginning to fully decode. One of the most intriguing aspects of these faint blue galaxies is their potential to illuminate the formation of the first supermassive black holes. Supermassive black holes, the behemoths at the centers of many galaxies, are believed to have formed in the early universe and played a crucial role in shaping galaxy formation. As we study galaxies at the edge of the observable universe, we begin to gather evidence that may suggest these supermassive black holes are closely tied to the growth and evolution of galaxies. The connection between the rate of star formation and the development of a supermassive black hole could provide key insights into how galaxies grow and change over time. This link between galaxies and black holes is still a subject of intense research, but the faint blue galaxies might hold some of the answers. As they are actively forming new stars, they are also likely to be hosting massive amounts of gas in their centers, gas that could eventually funnel into a supermassive black hole, triggering intense periods of growth. Understanding this relationship between star formation and black hole growth could help us uncover the mechanisms that govern the evolution of galaxies throughout cosmic history. Moreover, the study of these distant galaxies contributes to our understanding of the dark ages of the universe. The period of cosmic history between the Big Bang and the formation of the first stars, known as the cosmic dark ages, is an era that remains shrouded in mystery. By observing faint blue galaxies, we can gain insights into the transition from this dark age to the bright, star-filled universe we see today. As these galaxies are some of the youngest and most active, they provide a glimpse into the conditions that allowed the first stars to shine and illuminate the universe. The detection of faint blue galaxies also raises important questions about the limits of the observable universe itself. Currently, our observations are limited by the speed of light and the age of the universe. The further we look, the more we are looking into the past. The faint blue galaxies at the edge of the observable universe are some of the most distant objects we can observe, and the light that reaches us from these galaxies has been traveling for billions of years. But what lies beyond the reach of our telescopes? Is there more to the universe than we can currently see? These questions challenge the very limits of our knowledge, and they hint at the possibility of discoveries yet to be made, far beyond the observable horizon. In addition to these scientific implications, the study of faint blue galaxies also invites us to reflect on our place within the universe. We are, after all, observing galaxies that existed long before our planet, let alone our species, came into existence. The fact that we can peer back in time and glimpse the birth of galaxies challenges our understanding of time itself. It forces us to confront the vastness of the universe and our fleeting place within it. And yet, in this enormous cosmos, we find ourselves connected to the very same processes that birthed these distant galaxies. The atoms that make up our bodies were once forged in the cores of stars that came before us, stars that lived and died long before the Earth was even formed. In this way, the study of galaxies, no matter how distant, is a study of our own origins, a reminder that we are part of the same cosmic story that began billions of years ago. As our technology advances, so too does our ability to study galaxies at increasingly greater distances. Instruments like the James Webb Space Telescope, with its advanced infrared capabilities, are already helping scientists look further into the universe than ever before. With its ability to detect the faintest of light, even from the most distant galaxies, what promises to open up new frontiers in our understanding of cosmic history. By studying galaxies at the edge of the observable universe, we can gain an unprecedented view of the universe's infancy, allowing us to refine our models of galaxy formation, star evolution, and the dynamics of cosmic growth. The faint blue galaxies that we see today are not static. They are dynamic and constantly evolving. They may not appear the same way in the future. Their stars may age, burn out, and eventually die, leaving behind remnants of their once bright existence. But just as stars have life cycles, so too do galaxies. The faint blue galaxies we see now could eventually evolve into more mature, redder galaxies, similar to those we see closer to home. Over billions of years, the processes of star formation will slow down, and the galaxies will settle into a new phase of their existence, one marked by the cooling of their stellar population and the gradual cessation of new star formation. This inevitable transformation is a reminder of the ongoing evolution of the universe, a universe that is always in flux, always changing, and always giving rise to new phenomena. In the future, it's possible that the faint blue galaxies at the edge of the observable universe could offer even more profound revelations. As our instruments become more sensitive and our understanding of cosmic processes deepens, we may discover new patterns and connections that were previously invisible. We might learn, for instance, that the formation of faint blue galaxies is tied to larger-scale cosmic events that we are only beginning to comprehend. We might uncover new forms of matter or energy that influence the behavior of galaxies on cosmic scales, or we could identify previously unseen structures within the galaxies themselves, providing new insights into how galaxies interact with one another. Moreover, the discovery of new faint blue galaxies could force us to rethink our models of the early universe. If these galaxies were even more common in the distant past than we currently believe, it would suggest that the process of galaxy formation in the early universe was far more complex and rapid than previously thought. This would prompt a reevaluation of our understanding of cosmic evolution and the underlying mechanisms that govern the universe's development. The future of studying faint blue galaxies at the edge of the observable universe is filled with promise. Each new discovery has the potential to reshape our understanding of the cosmos, bringing us closer to answering some of the most fundamental questions about the nature of reality itself. From the formation of galaxies to the role of dark energy, from the evolution of stars to the mysteries of black holes, the study of these distant galaxies offers a wealth of opportunities for discovery. And as we continue to push the boundaries of our understanding, we are reminded that, no matter how far we look, there is always more to explore. The faint blue galaxies at the edge of the observable universe are just the beginning of what promises to be an exciting journey into the depths of space and time, a journey that will continue to reveal new wonders and challenge the limits of our imagination. As we continue exploring the faint blue galaxies at the edge of the observable universe, it becomes clear that these distant cosmic objects are not only fascinating in their own right, but also pivotal to understanding the very fabric of the universe. Each new discovery, each faint light captured from these galaxies, acts as a window into an epoch-long past, providing us with clues about the earliest moments of cosmic history. These galaxies, with their youthful glow and active star-forming regions, represent the formative stages of galaxy evolution, stages that were previously hidden from our view. One of the most intriguing aspects of the faint blue galaxies is their potential to answer questions about the dark matter that makes up most of the mass in the universe. Dark matter, although invisible to our eyes, has been inferred from its gravitational effects on visible matter. It is believed to play a crucial role in the formation of galaxies and their structures. As we study the faint blue galaxies, we hope to uncover how dark matter has influenced their development. These galaxies, some of the youngest and most distant we can observe, could hold the key to understanding how dark matter shaped the universe in its infancy. By analyzing their mass distribution and comparing them with simulations that take dark matter into account, scientists may be able to build a more detailed picture of how this mysterious substance affects galaxy formation. The faint blue galaxies also raise questions about the role of metal enrichment in the early universe. Metals, in the context of astrophysics, refer to elements heavier than hydrogen and helium. The process by which stars forge heavier elements in their cores and release them into the interstellar medium through supernova explosions is a key factor in the evolution of galaxies. The more metal-rich a galaxy becomes, the more likely it is to have formed stars with a broader range of properties, including those capable of supporting the conditions needed for life. By studying the chemical composition of the faint blue galaxies, astronomers can gain insights into the chemical evolution of the early universe. How quickly did these galaxies enrich their environments with metals? Did this process occur before the first galaxies reached their full potential, or is it still in its nascent stages? As we probe deeper into the mysteries of the faint blue galaxies, we also begin to question the broader implications of what we're seeing. These galaxies exist in an era of the universe when conditions were dramatically different from what we observe today. The universe was much smaller, denser, and hotter when these galaxies were young, yet their existence suggests that the basic processes of star formation and galaxy evolution were already in motion. This brings us to one of the most profound questions: is the process of galaxy formation universal, or is it shaped by the specific conditions of time and space in which galaxies form? The faint blue galaxies may offer a glimpse into the answer. Moreover, these distant galaxies challenge our assumptions about the way we think about the evolution of the universe. The current paradigm of galaxy formation is based largely on models of hierarchical assembly, where smaller galaxies merge to form larger ones over time. However, the faint blue galaxies suggest that this process may not be as simple as it seems. Some of these galaxies appear to be forming in isolation, rather than through mergers, which could indicate that the process of galaxy formation is more diverse than we previously thought. If we can uncover more about these galaxies, we may have to revise our understanding of how galaxies form and evolve on large scales. The observation of faint blue galaxies has also sparked a renewed interest in the concept of cosmic reionization. Reionization is the process by which the universe transitioned from being opaque to transparent, as the first stars and galaxies began to form and emit radiation. The faint blue galaxies that we see at the edge of the observable universe may be key players in this process. By studying their properties, such as their stellar population and the amount of ultraviolet light they emit, scientists can learn more about the timeline of reionization and the role that these galaxies played in this dramatic phase of cosmic evolution. This discovery also intersects with our growing understanding of the expansion of the universe. The further away a galaxy is, the older its light is, meaning we're looking at a snapshot of a time long past. The faint blue galaxies at the very edge of the observable universe are among the most distant objects we can study, and this allows us to probe the universe at a time when it was much younger and still undergoing rapid expansion. By observing these galaxies and comparing their characteristics with closer, more evolved galaxies, we can track how the universe has expanded and evolved over billions of years. As the technology we use to observe these galaxies continues to improve, our ability to study them in greater detail will only increase. The James Webb Space Telescope, with its unparalleled infrared sensitivity, will allow us to peer even further into the distant past, uncovering galaxies that are even fainter and further away than we can currently detect. The next generation of telescopes, such as the Extremely Large Telescope, ELT, and the Giant Magellan Telescope, GMT, will further push the boundaries of what we can see, revealing galaxies that existed even earlier in the universe's history. These advancements will undoubtedly open up new avenues of exploration, giving us a clearer picture of how galaxies form, evolve, and interact with one another. In this sense, the study of faint blue galaxies is not just a quest to understand the past, but also an exploration of the future. With each new discovery, we move closer to unlocking the secrets of the universe. These galaxies, though distant and faint, are providing us with a wealth of information about the processes that shape the cosmos, the role of dark matter and dark energy, and the evolution of the very building blocks of the universe itself. Their study is pushing the boundaries of our knowledge, expanding our understanding of the universe, and challenging our perceptions of time, space, and reality. The faint blue galaxies at the edge of the observable universe are far more than just distant cosmic objects. They are the keys to unlocking some of the greatest mysteries of the cosmos, from the nature of dark matter and dark energy to the processes that govern galaxy formation and evolution. By studying these galaxies, we are not only uncovering the history of the universe but also exploring the future of cosmic discovery. As we continue to probe deeper into the universe's past, we will undoubtedly uncover more secrets that will challenge our understanding and expand our view of the cosmos. These galaxies, as faint and distant as they may seem, are the shining beacons of the universe's greatest mysteries, mysteries that we are just beginning to unravel. In environments with fewer metals, gas cools less efficiently, and the dynamics of star formation change dramatically. Stars born in such conditions may be more massive on average, burning hotter and faster than their metal-rich counterparts. This means the early universe may have been dominated by large, short-lived stars that exploded as supernovae shortly after forming, rapidly enriching their surroundings with new elements. This cycle of birth, death, and enrichment was critical in setting the stage for the formation of more stable galaxies, stars, and eventually, planetary systems capable of supporting life. These intense early processes are what shaped the eventual diversity of galaxies we observe today. The faint blue galaxies act as a kind of laboratory where astronomers can test theories about how these first cycles of star formation and metal enrichment took place. By comparing their properties, such as size, mass, and composition, with more evolved galaxies closer to us, we can trace the developmental pathways galaxies have followed across billions of years. Moreover, these galaxies may help us refine our understanding of cosmological models, including how the cosmic web, the vast, filamentary structure of matter in the universe, developed. Faint blue galaxies are often found in regions that eventually became nodes of this web, clustering together as gravity pulled matter into denser structures. Studying their distribution can reveal how dark matter shaped the scaffolding of the universe. When plotted across the sky, their positions and velocities trace the underlying gravitational framework that ties the cosmos together. In observing these faint blue galaxies, astronomers are not only seeing the building blocks of modern galaxies but also catching glimpses of an era where the rules of cosmic evolution were still being written. Each one is like a fossil preserved in light, a beacon from a time when the universe was just a few billion years old, or younger. Their brightness in the blue and ultraviolet spectrum is a direct consequence of intense star-forming activity. These young, hot stars emit shorter wavelengths of light, which are then stretched and redshifted as the universe expands. By the time this light reaches us, it has traversed unimaginable distances and billions of years, carrying with it the signature of its origin. What's even more astonishing is how these galaxies help anchor our measurements of cosmic time and space. They serve as reference points for calibrating the expansion rate of the universe. By comparing their redshifts, how much their light has been stretched, with their actual distances, cosmologists refine calculations for the Hubble constant. However, discrepancies between different measurements have led to the so-called Hubble tension, a growing debate in cosmology. Faint blue galaxies, especially those with precisely measured redshifts, offer a possible path forward in resolving this mystery by acting as neutral benchmarks. These galaxies also illuminate a critical phase known as cosmic dawn, the period in the universe's history when the first stars and galaxies formed. Before this era, the universe was filled with a dense fog of neutral hydrogen that absorbed light. As the first stars ignited and began emitting intense ultraviolet radiation, they reionized the hydrogen, gradually clearing the fog in a process known as reionization. Faint blue galaxies are believed to be key contributors to this process, pumping out high-energy photons that reshape the cosmic landscape. By studying their spectra, astronomers can infer how much ionizing radiation they emitted and estimate their cumulative impact on reionization. Furthermore, these galaxies offer clues about the evolution of galactic morphology. While many nearby galaxies exhibit complex spiral arms or elliptical structures, faint blue galaxies often appear irregular and chaotic. This lack of structure suggests that they are still undergoing gravitational interactions, mergers, and internal turbulence. Their shapes are not yet settled. Studying their irregular forms allows scientists to piece together how galaxies grow, collide, and eventually stabilize into more mature configurations. This chaotic beauty, though visually unrefined, is rich with information about the physical processes at work during the universe's most formative years. High-resolution imaging from telescopes like the James Webb Space Telescope and the Hubble Space Telescope has begun to resolve the faint light from these distant objects into discrete structures, clumps of stars, streams of gas, and hints of dark matter halos. These observations reveal that even the smallest, most unassuming galaxies may play outsized roles in cosmic evolution. Some of them could be proto-galaxies, the seeds from which massive galaxy clusters later formed. Others might be survivors, isolated systems that have remained untouched by galactic mergers and interactions for billions of years. The chemical composition of these galaxies is another source of insight. With spectroscopy, astronomers break down the light from faint blue galaxies into its component wavelengths, revealing the presence, or absence, of various elements. The ratios of hydrogen, helium, oxygen, and nitrogen provide a kind of fingerprint, telling us how many generations of stars a galaxy has hosted. Low metallicities confirm that we're observing relatively pristine systems, perhaps containing some of the first stars ever formed. These ancient environments serve as a testing ground for theories about nucleosynthesis and stellar evolution under primordial conditions. What's also fascinating is the apparent variation in star formation rates among these distant galaxies. Some are undergoing explosive bursts of activity, while others seem more subdued. This inconsistency raises questions about the triggers for star formation in the early universe. Are these bursts caused by mergers, tidal forces, or variations in the intergalactic medium? Or are they the result of internal dynamics, such as feedback from supernovae or nascent black holes? As we gather more data, patterns begin to emerge, but many mysteries remain. The diversity among faint blue galaxies hints at a cosmic environment that was far more complex and dynamic than previously assumed. Additionally, these galaxies may hold the key to understanding the origin of cosmic dust. Dust in astronomy refers to tiny grains of elements like carbon and silicon, formed in the atmospheres of aging stars and in the remnants of supernovae. Dust plays a vital role in shielding molecules from harsh radiation, enabling the formation of planets and organic chemistry. Yet, detecting dust in such distant galaxies is a technical challenge. When dust is found in galaxies that are only a few 100 million years old, it implies that star formation and stellar death cycles happened incredibly fast, faster than some models allow. This forces scientists to reconsider timelines and mechanisms for dust production. The role of gravitational lensing has also become crucial in observing these distant galaxies. When a massive object, such as a galaxy cluster, lies between Earth and a faint background galaxy, it can bend and magnify the light from that distant source, a phenomenon predicted by Einstein's theory of general relativity. This cosmic magnification allows astronomers to study galaxies that would otherwise be too faint to detect. Thanks to gravitational lensing, we've been able to observe some of the most distant and dimmest galaxies ever recorded, revealing details about their structure and composition that would be impossible to gather otherwise. Equally important is the challenge of simulating faint blue galaxies in cosmological models. Astrophysicists use computer simulations to recreate the universe's evolution from the Big Bang to the present day. These models must accurately produce the properties of faint blue galaxies: number, size, brightness, and distribution, if they are to be trusted. But many simulations have struggled to match observations, particularly when it comes to reproducing the precise mix of small, star-forming galaxies seen at high redshifts. As a result, the study of these galaxies has forced significant revisions in simulation parameters, such as the efficiency of star formation, the strength of feedback mechanisms, and the behavior of dark matter. From an observational standpoint, pushing the limits of detection is a monumental task. These galaxies are not just distant, they're also incredibly dim. Capturing their light requires long exposure times and sensitive instruments that can detect the faintest glimmers. In some cases, a single image may take dozens of hours to collect. Even then, separating genuine galaxies from noise or foreground objects is a painstaking process. It's a testament to the ingenuity of astronomers and engineers that we can even see these objects at all, let alone analyze them in such detail. Their successful detection is a triumph of technology, mathematics, and human curiosity. And the philosophical implications of these galaxies cannot be overstated. Every photon from a faint blue galaxy represents a message sent across cosmic time, a reminder that we are part of something vast, ancient, and ongoing. The very act of observing these galaxies is an exercise in time travel, a way of witnessing the earliest moments of creation. In their faint light, we see echoes of beginnings, of stars igniting for the first time, of galaxies assembling from the chaos of the early universe, and of a cosmos that, against all odds, gave rise to conscious beings capable of wondering where it all came from. The James Webb Space Telescope, JWST, has become instrumental in this research. Its advanced infrared capabilities allow it to peer further into the universe than any telescope before it, detecting galaxies whose light has been stretched into the infrared by billions of years of cosmic expansion. This means JWST is uniquely suited to study faint blue galaxies from the earliest epochs, galaxies that are now only visible as tiny smudges of redshifted light. By analyzing their spectra, astronomers can determine their composition, age, and rate of star formation, helping to build a more comprehensive picture of galaxy evolution across cosmic time. These faint galaxies are not just relics of the past, they're active engines of star production. Many of them form stars at rates much higher than galaxies in the nearby universe. This intense star-forming activity leads to what's called stellar feedback, a process where energy and matter from supernovae and stellar winds push against the gas in a galaxy, regulating future star formation. This feedback can either quench star formation by dispersing gas or trigger new star birth by compressing surrounding material. Studying how this feedback operates in these primitive galaxies helps astronomers understand how galaxies maintain balance and avoid forming too many or too few stars. Faint blue galaxies also present a paradox. Their star formation rates are incredibly high, and yet they remain small and relatively dim compared to more massive galaxies. This suggests that in the early universe, galaxies were forming stars with remarkable efficiency despite their limited mass. These early galaxies might be responsible for producing a significant fraction of the universe's stars, even though they are less conspicuous than their more massive counterparts. It's a case where the quiet, faint galaxies might actually have played a louder role in cosmic history than the giants. The study of these galaxies also provides insight into the interstellar medium, ISM, of the early universe. The ISM, the gas and dust between stars, plays a crucial role in the life cycle of a galaxy. It is the raw material from which stars form and is continually reshaped by the feedback from stellar activity. In faint blue galaxies, the ISM tends to be more pristine, containing fewer metals and dust grains. This makes it an excellent environment for studying the primordial conditions of galaxy formation, allowing researchers to see how the first structures emerged from a simpler, more fundamental universe. One of the remarkable discoveries from these faint galaxies is the presence of clumpy star-forming regions. Unlike the organized spiral arms of mature galaxies, these early systems often have irregular, chaotic shapes with bright knots of intense star formation scattered throughout. These clumps are thought to form from gravitational instabilities in the galaxy's disk or from merging with other small galaxies. Their presence suggests that galaxy assembly in the early universe was a violent, dynamic process, marked by collisions, fragmentation, and rapid growth. Over time, many of these clumpy galaxies likely merged with one another, gradually coalescing into the larger, more structured galaxies we see in the local universe. This hierarchical model of galaxy formation, where small objects merge to form larger ones, is a cornerstone of cosmological theory. By examining the properties of faint blue galaxies, scientists are able to test and refine this model. For instance, the number of mergers, the timing, and the resulting structures all help calibrate simulations of cosmic evolution. In addition to mergers, cold gas accretion also plays a key role in fueling star formation in these galaxies. In the early universe, streams of cold hydrogen gas flowed along the cosmic web, feeding young galaxies and allowing them to sustain rapid star formation. These filaments of gas were like lifelines, delivering the fuel necessary for growth. Observations of faint blue galaxies give us indirect evidence of this accretion process, such as extended halos of hydrogen and unusual kinematic signatures that hint at gas inflow. These galaxies also help trace the timeline of cosmic chemical evolution. As stars go through their life cycles, they produce heavy elements that get dispersed into the surrounding environment. Over time, galaxies become more enriched, transitioning from low metallicity systems to the metal-rich galaxies we see today. By comparing the metallicity of faint blue galaxies at different redshifts, astronomers can map out how quickly the universe built up its elemental diversity. This has implications not only for galaxy evolution, but also for the formation of planets, and potentially life itself. Interestingly, many of the faint blue galaxies show signs of being compact, with dense cores that may eventually evolve into the bulges of larger galaxies. These compact, high-density regions are the birthplaces of stellar spheroids and may even harbor the seeds of supermassive black holes. Although detecting black holes in such distant, faint systems is extremely difficult, some models suggest that the intense activity in these early galaxies could give rise to the first massive black holes, which would later anchor galaxies like the Milky Way. Understanding these early structures also helps constrain theories about dark energy, the mysterious force driving the accelerated expansion of the universe. The distribution and growth rate of galaxies at high redshift provide data points that cosmologists use to infer the behavior of dark energy over time. If the expansion history deviates from predictions, it could indicate that our understanding of dark energy, or gravity itself, is incomplete. Faint blue galaxies serve as markers along the timeline of expansion, allowing scientists to measure how the universe has grown and stretched. Perhaps one of the most philosophically compelling aspects of studying faint blue galaxies is the realization that we are looking into the deep past, not just in years, but in fundamental epochs. The light from these galaxies began its journey long before Earth existed, long before our solar system formed, and even before many of the elements that make up our bodies were synthesized. In a sense, when we observe them, we're not just seeing across space, we're seeing across time itself. The pursuit of understanding these galaxies is a journey through the limits of our perception, instrumentation, and imagination. They challenge us to ask bigger questions. How did everything we know come to be? What forces shaped the universe into its current form? And are we missing pieces of the puzzle that only these faint whispers from the cosmos can provide? This raises important questions about how such galaxies gathered their gas and sustained these bursts of star formation. One prevailing theory suggests that streams of cold gas from the cosmic web continuously flowed into these galaxies, fueling rapid stellar growth. Unlike modern galaxies, which often acquire gas through mergers or recycling of their own material, these early galaxies may have relied heavily on pristine gas directly from the intergalactic medium. This mode of gas accretion could have contributed to their low metallicities and relatively simple chemical compositions. Another critical area of study is how these galaxies interact with their environment. Faint blue galaxies often appear in dense protoclusters, regions that will eventually evolve into massive galaxy clusters. Their interactions with neighboring galaxies and the surrounding dark matter structures may play a key role in shaping their morphology, spin, and star formation history. Some may undergo mergers that rapidly transform them into larger systems, while others might be stripped of gas and halted in their development. These environmental effects are essential for understanding the wide diversity of galaxies we see today. The morphology of faint blue galaxies is also a fascinating subject. Many exhibit irregular or clumpy structures, lacking the organized spirals or elliptical shapes of more mature systems. These chaotic forms hint at the turbulent processes shaping them: collapsing gas clouds, active star-forming regions, and gravitational interactions all combine to produce their fragmented appearance. These clumpy regions are often the brightest spots in the galaxy, each potentially the site of intense stellar nurseries where massive stars are born in quick succession. Some of these galaxies also show signs of central black holes, albeit much smaller than the supermassive ones found in larger galaxies today. The presence of these intermediate mass black holes raises compelling questions about their origin. Did they form from the direct collapse of massive gas clouds, or did they grow from smaller seed black holes born in the depths of the first stars? Faint blue galaxies may contain the missing link in our understanding of black hole evolution, providing a bridge between stellar mass black holes and the titanic ones anchoring galactic cores today. Observations have revealed that many of these galaxies are surprisingly compact. Their light may be faint, but their star-forming regions are often densely packed, sometimes only a few hundred light-years across. This extreme compactness suggests that conditions within these galaxies are unusually intense, with high pressures, strong magnetic fields, and violent stellar winds. It's an environment very different from the more sedate star-forming regions in nearby galaxies like the Milky Way. Understanding how stars form under these extreme conditions could yield new insights into the physics of star formation itself. Despite their low mass, faint blue galaxies may have had an outsized influence on the structure of the universe. Their energetic outflows of gas and radiation can travel great distances, enriching the intergalactic medium with metals and altering the temperature and ionization state of the surrounding space. These galactic winds may even trigger the formation of new galaxies by compressing nearby gas clouds. As such, they act as both creators and destroyers, sculpting the cosmic landscape around them. Cosmologists also use these galaxies as probes of the universe's expansion and structure. Their light, passing through vast tracts of space, is subtly distorted by the gravitational influence of matter along the way, a phenomenon known as weak gravitational lensing. By measuring these distortions, researchers can map the distribution of dark matter, which otherwise remains invisible. Faint blue galaxies, due to their sheer abundance and reach into the distant universe, provide a rich dataset for this kind of analysis. Interestingly, these galaxies also challenge current models of galaxy formation. Simulations often struggle to produce the exact number and properties of faint blue galaxies observed. This discrepancy has led to the refinement of feedback models, star formation recipes, and even the initial conditions used in large-scale simulations like Illustris or Eagle. As observational data improves, especially with instruments like JWST, these models will either be confirmed or forced to evolve further, potentially uncovering new physics in the process. Some scientists speculate that studying these galaxies might even shed light on exotic phenomena. For instance, if the early universe had different properties, such as variations in fundamental constants, or the influence of yet undiscovered particles, these galaxies would reflect those differences in their formation and behavior. Although such theories remain speculative, the data from faint blue galaxies serve as a critical testing ground for ideas that lie beyond the current standard model of physics. The colors of these galaxies are also telling. Their blue hue, caused by an abundance of young, hot stars, slowly fades as they age and star formation declines. Over billions of years, many of these galaxies may evolve into red, elliptical systems with little ongoing star formation. Others may merge into larger spiral galaxies or be consumed entirely. Tracking their life cycle across cosmic time is essential for building a complete narrative of how galaxies form, grow, mature, and die. Faint blue galaxies provide a humbling reminder of our place in the universe. Each one represents a self-contained system of stars, gas, dust, and possibly planets, evolving independently for billions of years. To detect them, let alone analyze them, speaks to the extraordinary capabilities of modern astronomy. But it also hints at how much more there is left to discover. For every faint galaxy we've observed, countless others remain just beyond the reach of our instruments. Tiny sparks of light still waiting to be found. Furthermore, the chemical composition of these galaxies is another window into their early nature. Spectroscopic observations show that many faint blue galaxies are extremely metalpoor, meaning they contain few elements heavier than hydrogen and helium. This supports the idea that they are among the first systems to experience significant star formation. Metals are forged in the hearts of stars and dispersed into the interstellar medium through stellar winds and supernovae, so their absence indicates that these galaxies haven't undergone many generations of stellar evolution. Studying the metallicity of these galaxies helps researchers determine just how young they are in cosmic terms and whether they could be remnants of the earliest epochs of galaxy formation. In many cases, astronomers use the ratio of oxygen to hydrogen in a galaxy's emission lines to estimate its metallicity. A lower ratio suggests a younger system with fewer processed elements. This is important because it allows scientists to distinguish between truly primordial galaxies and more evolved galaxies that merely appear faint due to their distance. By cataloging thousands of these faint blue systems, researchers can build a statistical framework that illustrates the pace at which the universe enriched itself with heavier elements. Gravitational lensing is another powerful tool in this investigation. When a massive foreground object like a galaxy cluster bends the light of more distant objects, it can magnify the background light, allowing astronomers to detect galaxies that would otherwise be too faint. Many of the most detailed images we have of faint blue galaxies come from gravitational lensing, including several identified in the Hubble Frontier Fields and by JWST. These magnified galaxies offer unique opportunities to study small-scale structures and star-forming regions in unprecedented detail, shedding light on how these early systems were built. Lensing also helps overcome a major observational challenge: the intrinsic faintness of these galaxies. Because they are so distant, and because their light is spread over billions of years of travel, their brightness is extremely low. Without lensing or next-generation instruments like JWST, most would be invisible to our current telescopes. Even with advanced technology, astronomers often must integrate light for hours or days just to tease out a signal from these ghostly sources. But every successful detection adds another piece to the puzzle of the early universe. The shapes and sizes of these galaxies are equally intriguing. Most of them appear compact, often just a few hundred parsecs across, and are dominated by scattered clumps of bright star formation. These clumps can be hundreds of times more luminous than similar regions in nearby galaxies, suggesting extremely efficient star formation. Their irregular structures suggest a dynamic, chaotic environment dominated by rapid gravitational collapse and violent stellar feedback. Over time, these clumpy systems may have merged and evolved into the more ordered spiral and elliptical galaxies we see in the modern universe. Computer simulations have become an invaluable companion to observational data in this field. Advanced cosmological simulations like Illustris, Fire, and Eagle attempt to model the formation and evolution of galaxies from the Big Bang to the present day. These simulations incorporate physical laws governing gravity, hydrodynamics, star formation, and feedback. When their results match the characteristics of faint blue galaxies observed in the real universe, scientists gain confidence in the underlying models. But mismatches, such as too many or too few galaxies, or discrepancies in metallicity, help refine and improve these theories. One of the great challenges is reproducing the abundance of faint blue galaxies seen at high redshift. Some simulations struggle to account for the number of low-mass, highly star-forming galaxies that appear in deep field surveys. This discrepancy may point to missing physics in the models, perhaps related to gas cooling, feedback processes, or the nature of dark matter. Ongoing improvements in computational power and resolution are helping to close this gap, but the faint blue galaxies still hold surprises that defy easy explanation. The colors of these galaxies, particularly their signature blue hue, are also meaningful. Blue light in galaxies typically comes from young, hot stars that burn at higher temperatures. These stars are short-lived, so the prevalence of blue indicates recent and ongoing star formation. However, because these galaxies are so distant, their light has been redshifted into the infrared by the expansion of the universe. JWST's infrared instruments are essential for detecting the light that originally left these galaxies in the ultraviolet and visible part of the spectrum. It's also important to note that not all faint galaxies at the edge of the observable universe are blue. Some appear red or even invisible in certain wavelengths, possibly due to dust obscuration or older stellar populations. Understanding the diversity of faint galaxies is key to assembling a complete timeline of galaxy evolution. The blue ones may represent a phase of rapid growth, while redder or dimmer ones may be transitioning into quiescence or fading into obscurity. Each galaxy type tells a different story, contributing to the overall narrative of cosmic development. The study of faint blue galaxies isn't just about understanding galaxies, it's about understanding ourselves and our place in the cosmos. The stars in these early galaxies forged the first elements heavier than helium, carbon, oxygen, nitrogen, some of which would eventually find their way into planets, oceans, and life itself. By studying how and when these elements were made, astronomers can trace the ancestry of the atoms that make up our own bodies. It's a humbling connection that stretches across space and time. Despite all we've learned, vast mysteries remain. Are these faint galaxies typical of their era, or are we seeing only a biased subset due to observational limits? How did such small systems produce stars so efficiently, and why did they eventually fade? What role did they play in the overall architecture of the universe we inhabit today? As technology advances and new data pours in, we edge closer to answers, but the faint blue galaxies continue to whisper secrets from the dawn of time. As astronomers peer deeper into these ancient light sources, they also study the ionization states of the gas within them. The presence of ionized hydrogen and oxygen lines tells us that high-energy photons are flooding these galaxies, likely from young, massive stars. These photons are capable of stripping electrons from atoms, leaving behind ionized regions in the surrounding gas. The ratio of these ionized lines provides critical insight into the age and intensity of the star-forming processes taking place in these galaxies. In some cases, the spectra of faint blue galaxies suggest that the star formation is so intense that it has driven large amounts of gas out of the galaxy, a process known as galactic feedback. This can hinder the ability of the galaxy to form stars in the future, effectively quenching its growth. These insights are helping to refine our understanding of the transition from the cosmic dark ages to the well-lit universe we see today. The cosmic dark ages represent the period after the Big Bang but before the first stars and galaxies formed. During this era, the universe was essentially filled with neutral hydrogen gas. The light emitted by the first stars began to ionize this gas, marking the end of the dark ages. Studying faint blue galaxies gives us a direct window into this transition. Because these galaxies are among the earliest to form, they can provide clues to how and when the first stars began to shine and how the universe began to fill with light. The role of these galaxies in reionizing the universe is a subject of great interest. It's thought that the process of reionization, which happened about 13 billion years ago, was driven by the energetic radiation from young galaxies. As these galaxies formed, their intense ultraviolet light stripped electrons from the hydrogen atoms in the surrounding space, turning the neutral hydrogen gas into ionized plasma. By examining the properties of faint blue galaxies, astronomers can learn more about this process. For example, the age of the star populations, the amount of gas present, and the rate of star formation in these galaxies all provide crucial information on how quickly and efficiently reionization occurred. Interestingly, the detection of faint blue galaxies at such extreme distances also reveals something remarkable about the universe's expansion. The light from these galaxies has been traveling for billions of years, and as it has journeyed toward Earth, it has been stretched out due to the expansion of space itself. This phenomenon, known as cosmological redshift, causes the light to shift to longer wavelengths, moving from the ultraviolet and visible parts of the spectrum into the infrared. As a result, when we look at faint blue galaxies, we are seeing light that has been redshifted, offering a glimpse into the conditions of the early universe. This gives astronomers a way to study the universe's evolution, from a time when it was much smaller and denser, to its current state. Despite their importance, detecting these faint blue galaxies is not an easy task. As mentioned, these galaxies are incredibly distant, and their light is extremely faint by the time it reaches Earth. The expansion of the universe means that the wavelengths of this light are stretched, and by the time it reaches us, it is often far too faint to detect with traditional telescopes. To overcome this challenge, astronomers rely on some of the most advanced instruments available, such as the Hubble Space Telescope and, more recently, the James Webb Space Telescope. These telescopes can detect infrared light, allowing scientists to observe the faintest objects in the universe, including distant galaxies that would otherwise be invisible. In addition to these telescopes, astronomers also rely heavily on computational models and simulations to predict where these galaxies might be located. The most advanced simulations of cosmic structure formation take into account the effects of dark matter, dark energy, and the gas dynamics that influence galaxy formation. These models help astronomers pinpoint areas in the sky where faint blue galaxies are likely to exist, allowing them to target their observations more effectively. One of the most surprising aspects of studying faint blue galaxies is how much they can tell us about the environment in which they exist. These galaxies are often surrounded by large, diffuse clouds of gas and dust. The interaction between these galaxies and their surroundings can have a significant impact on their development. For example, in regions of space where the density of gas is high, galaxies may experience a higher rate of star formation due to the increased availability of raw material. On the other hand, galaxies located in more isolated regions may have a slower rate of star formation, as they have fewer resources to draw from. Moreover, these faint blue galaxies also interact with one another. Although they are often seen as isolated, many of these galaxies are in the process of merging or interacting with nearby systems. This is a common feature in the early universe, where smaller galaxies would collide and merge to form larger ones. These interactions can trigger bursts of star formation, often referred to as starburst events, which are some of the most energetic and spectacular phenomena observed in distant galaxies. Studying these interactions provides insight into the processes that led to the formation of the larger galaxies we see today. In the distant future, we may also learn more about the long-term evolution of these galaxies. As they continue to form stars and interact with their surroundings, they may evolve into the massive galaxies observed in the local universe. These galaxies may undergo a variety of changes over billions of years, transitioning from irregular, star-forming systems to more stable, quiescent galaxies. The study of faint blue galaxies offers a glimpse into this evolutionary process, providing a snapshot of the universe at a critical juncture in its development. The ultimate question remains: will these faint blue galaxies eventually merge into the great cosmic structures we see today, or will they fade away, leaving behind only the remnants of their star formation? The answer to this question will help to clarify our understanding of galaxy evolution, star formation, and the history of the universe itself. Each new discovery about these galaxies brings us one step closer to understanding the vast, intricate tapestry that makes up the cosmos. But as our observations push further into the universe's past, one thing is clear: the faint blue galaxies at the edge of the observable universe hold secrets that could forever change our understanding of the cosmos. As astronomers continue their quest to understand the faint blue galaxies at the edge of the observable universe, they also face significant challenges in terms of data acquisition and interpretation. The light from these distant objects takes billions of years to reach Earth, meaning that the image we see is not a real-time snapshot but a view of how the galaxy appeared billions of years ago. This means that the current state of these galaxies may be vastly different from what we observe today. By the time the light from these galaxies reaches us, they could have already undergone significant changes due to cosmic events such as mergers, supernovae, or shifts in star formation rates. One of the greatest challenges faced by astronomers is determining the exact distance to these galaxies. As mentioned, the farther away an object is, the fainter it appears. This means that measuring the distance accurately becomes increasingly difficult as we observe galaxies further and further away. Standard methods of measuring distance, such as redshift or Cepheid variable stars, become less effective at these extreme distances. Instead, astronomers rely on more indirect methods, such as studying the characteristics of the light emitted by these galaxies, or by using the cosmic distance ladder, which involves comparing objects at different distances and using their known properties to estimate distances. A particularly intriguing aspect of faint blue galaxies is their star formation rates. As mentioned earlier, these galaxies often exhibit rapid, intense bursts of star formation. But the key question is, why? What triggers these explosive periods of star creation, and how do they sustain themselves over long periods of time? Some theories suggest that the formation of these galaxies is driven by the collapse of gas clouds, which is an incredibly efficient way of producing new stars. When a cloud of gas becomes dense enough, the gravitational pull causes it to collapse, triggering a chain reaction that leads to the birth of new stars. Another factor contributing to the high rate of star formation in these galaxies could be their isolation in the early universe. In more crowded regions, galaxies often interact with one another, and the gravitational forces at play can disrupt the normal processes of star formation. However, in isolated environments, galaxies are free to evolve on their own without the interference of neighboring objects. This allows them to focus their energy on star formation, leading to the rapid creation of new stars and the bright blue appearance of these galaxies. Despite their remarkable characteristics, the future of these faint blue galaxies remains uncertain. As the universe ages, galaxies gradually run out of the raw materials needed for star formation. The gas and dust that fuel the birth of new stars are slowly depleted, and without these resources, the rate of star formation slows down. Over billions of years, galaxies like these will likely evolve into more stable systems, where star formation occurs at a much slower rate. Eventually, the once vibrant blue galaxies will fade, their bright stars being replaced by older, dimmer stars, and their gas clouds dissipating into the vast void of space. However, the process is far from simple. Some galaxies undergo processes that can rejuvenate their star formation, triggering bursts of activity long after they have reached what would typically be considered the end of their life cycle. For instance, interactions with other galaxies can reignite the star formation process. These mergers and interactions can funnel gas into the center of galaxies, reigniting the engines of star formation. In the case of the faint blue galaxies, some may undergo such interactions and emerge from them as even more vigorous star-forming systems, potentially extending their periods of activity far beyond what we would typically expect. As we continue to explore the mysteries of faint blue galaxies, we are also beginning to appreciate the importance of studying these objects in conjunction with other cosmic phenomena. For instance, the role of supermassive black holes in galaxy evolution is increasingly seen as central to understanding the life cycle of galaxies, including faint blue galaxies. It is believed that many galaxies, including those at the edge of the observable universe, harbor supermassive black holes at their centers. These black holes can influence the star formation process by emitting powerful jets of energy and radiation that heat and expel the surrounding gas, preventing further star formation in some cases. Conversely, the accretion of material by these black holes can trigger bursts of star formation, leading to more intense periods of activity. The study of faint blue galaxies also intersects with the broader investigation into the nature of dark matter and dark energy. These mysterious components of the universe play a crucial role in the formation and evolution of galaxies, and understanding their effects is vital to our understanding of galaxy dynamics. Dark matter, in particular, is thought to influence the rotation and structure of galaxies, helping to hold them together. The gravitational effects of dark matter can also affect the gas clouds and star formation processes within these galaxies, making it a key factor in understanding their behavior. In addition, the study of faint blue galaxies provides valuable information about the early conditions of the universe. The first few billion years after the Big Bang were a period of intense change, as the first stars and galaxies formed and began to reshape the universe. By examining the properties of galaxies at this early stage, we can learn more about the processes that govern the formation of structures in the universe and how the cosmos evolved from a featureless expanse of gas and dust into the rich, complex system of galaxies we see today. Another exciting aspect of studying these galaxies is the potential for finding new, unusual types of objects within them. For example, faint blue galaxies are often associated with a wide range of exotic phenomena, such as extremely hot stars, unusual nebulae, and even rare types of black holes. The combination of high star formation rates and the complex dynamics within these galaxies creates a rich environment for the emergence of strange and unique cosmic objects. As technology continues to improve, we may uncover new and surprising phenomena that we have yet to imagine. As the field of extragalactic astronomy progresses, we will likely continue to uncover new galaxies at the very edge of the observable universe. These discoveries will help to refine our models of galaxy formation and evolution, and provide new insights into the earliest epochs of the universe. The study of faint blue galaxies at the edge of the observable universe is not only crucial for understanding the distant past but also for understanding the future of galaxies, including our own Milky Way. With the advent of next-generation telescopes, such as the James Webb Space Telescope and the Future Extremely Large Telescope, ELT, the study of faint blue galaxies will continue to provide a wealth of information. These instruments will enable astronomers to peer even further back in time, uncovering galaxies that are older, fainter, and more distant than any we have observed before. The hope is that by studying these galaxies, we can gain deeper insights into the fundamental processes that shape the universe. As we continue to observe faint blue galaxies at the edge of the observable universe, there is an increasing focus on how these distant objects can help us unravel the mysteries of cosmic history. One of the most significant questions that still remains unanswered is the exact process of galaxy formation during the very early universe. Understanding these faint blue galaxies provides a glimpse into the conditions that prevailed just a few 100 million years after the Big Bang. By observing their properties and behaviors, scientists are able to build more accurate models of the formation of the first galaxies and the role that stars played in shaping the universe as we know it. One of the key aspects of these early galaxies is their role in reionizing the universe. During the so-called epoch of reionization, which occurred around 500 million to 1 billion years after the Big Bang, the universe transitioned from being opaque to transparent. Prior to this, the cosmos was filled with a fog of neutral hydrogen that scattered light and prevented clear observation of distant objects. However, the formation of the first stars and galaxies played a critical role in ionizing the hydrogen gas, allowing light to travel freely through the universe. Faint blue galaxies, with their intense star formation, likely played an important part in this process, as the ultraviolet radiation emitted by their stars helped to ionize the surrounding gas. The study of these galaxies also ties into our broader understanding of the cosmic web. The universe is not randomly structured. Instead, galaxies tend to form in vast, interconnected filaments of dark matter and gas that make up what is known as the cosmic web. These filaments act as highways for galaxy formation, guiding the gas and dust into clusters that eventually evolve into galaxies. Faint blue galaxies, located in the distant reaches of the universe, are often found in the outskirts of these filaments, giving us crucial information about how galaxies form and evolve in relation to their surrounding cosmic environment. As the James Webb Space Telescope, JWST, continues to provide us with an unprecedented view of the distant universe, the role of faint blue galaxies will become even more important. The JWST is equipped with advanced instruments capable of observing infrared light, which allows it to peer deeper into space and further back in time than ever before. By observing faint blue galaxies with the JWST, scientists will be able to explore their structure, composition, and star formation processes in greater detail. This, in turn, will help us understand the mechanisms behind galaxy formation and evolution in the early universe, and how these galaxies contributed to the overall development of the cosmos. One of the exciting prospects of studying these distant galaxies is the possibility of finding clues about the formation of the first black holes. It is believed that supermassive black holes, which reside at the centers of many galaxies, played a pivotal role in the evolution of galaxies throughout the universe's history. However, the precise mechanisms by which these black holes formed remain uncertain. Did they grow from smaller black holes, or did they form directly from the collapse of gas clouds in the early universe? By studying the properties of faint blue galaxies and their central regions, we may gain new insights into the early stages of black hole formation and how they influenced the development of galaxies around them. The discovery of faint blue galaxies also raises intriguing questions about the nature of dark energy. This mysterious force is thought to be responsible for the accelerated expansion of the universe, but its exact nature remains one of the greatest unsolved mysteries in modern cosmology. Dark energy affects the overall structure and evolution of the universe, influencing the rate at which galaxies are separated and how they evolve over time. By studying the distribution of faint blue galaxies, scientists can examine how dark energy might be influencing the universe's expansion at different stages of cosmic history. This could provide vital clues that help us understand the broader forces at work in shaping the universe. Another fascinating aspect of these galaxies is the role they play in the larger picture of galaxy evolution. Many of the faint blue galaxies that we observe today are relatively young, having formed during the early epochs of the universe. As they age, they will undergo various evolutionary processes, such as the consumption of their gas reserves and the gradual slowing of star formation. Eventually, these galaxies will likely merge with other galaxies, creating larger and more complex structures. In some cases, they may transition from being blue, star-forming galaxies to being red, more passive systems that contain older stars and less gas. This process is part of the ongoing cycle of galaxy evolution, and studying faint blue galaxies gives us a snapshot of a crucial phase in this cycle. The study of faint blue galaxies is not only significant for understanding the distant past but also for our current place in the universe. Observing these galaxies helps us place our own galaxy, the Milky Way, within the larger cosmic context. The Milky Way, like many other galaxies, is thought to have undergone similar processes of formation and evolution. However, it is difficult to know precisely how our galaxy compares to those at the edges of the observable universe. By studying distant galaxies, we can better understand the factors that shaped our own galaxy, including the role of dark matter, dark energy, and the interplay between star formation and galactic mergers. One area of ongoing research is the search for the first generation of stars, often referred to as population 3 stars. These stars are thought to have formed from nearly pristine gas, with very little metal content, in the early universe. They are believed to have been much larger and hotter than the stars we see today, and their death could have triggered the formation of heavier elements, such as carbon, oxygen, and iron, which are essential for life as we know it. Faint blue galaxies, with their high rates of star formation and their position in the early universe, may provide key insights into the nature of these first stars and their role in the chemical evolution of the universe. Furthermore, these galaxies are a reminder of the vastness and mystery of the universe. Despite the advances in technology that allow us to peer deeper into space, there is still so much that remains beyond our reach. The discovery of faint blue galaxies at the edge of the observable universe challenges our understanding of space and time, forcing us to confront the limits of what we can observe and comprehend. As our instruments improve and our knowledge grows, the faint blue galaxies will continue to provide a window into the distant past and help us unravel the complex history of the universe. The study of these distant galaxies is also a testament to human curiosity and the drive to explore the unknown. The search for these galaxies, and the effort to understand their nature, pushes the boundaries of our scientific knowledge and challenges us to think in new and innovative ways. As we continue to explore the universe, we will undoubtedly make even more groundbreaking discoveries that will transform our understanding of the cosmos and our place within it. As we continue our journey into the realm of faint blue galaxies, it's essential to recognize the deep impact these discoveries have on our conceptualization of the universe. These galaxies, while distant, provide us with tangible links to the very beginning of the cosmos. Through their study, scientists have been able to reconstruct some of the earliest epochs of cosmic history, helping to fill in the blanks of the universe's evolution from a hot, dense state to the complex structures we observe today. Yet, despite all the advances made in observational astronomy, many aspects of these faint blue galaxies remain elusive, leaving open a multitude of questions to explore. One intriguing characteristic of these galaxies is their age. The faint blue galaxies at the edge of the observable universe are among the oldest galaxies we can observe. As light from these galaxies has taken billions of years to reach us, we are essentially looking back in time, witnessing these galaxies as they appeared just a few 100 million years after the Big Bang. This makes them invaluable to scientists attempting to understand the timeline of galaxy formation and evolution. These early galaxies are believed to be in a period of rapid star formation, a process known as galactic birth. The stars within these galaxies are some of the first generations to form, meaning they are crucial in understanding the early chemical composition of the universe. The study of faint blue galaxies is not just about looking back in time. It also offers a glimpse into how these galaxies will evolve in the future. While many of these galaxies are intensely blue due to the ongoing star formation, their color is likely to change as they age. As the stars exhaust their available fuel and the rate of star formation slows, these galaxies will begin to shift from blue to red, signaling a shift from a period of active star formation to one of relative quiescence. This process mirrors the evolution of galaxies like our own Milky Way, which has experienced a similar trajectory over the course of its existence. The future of these galaxies is not entirely predetermined, however. Some of them may undergo significant interactions with other galaxies. The process of galactic mergers is a common feature in the universe. Over billions of years, galaxies collide and merge, their stars intermingling and triggering new phases of star formation or the depletion of available gas. These mergers are a critical part of galaxy evolution, and faint blue galaxies, with their high rates of star formation and young stellar populations, are prime candidates for such interactions. The outcome of these mergers will dictate the ultimate fate of these galaxies, with some possibly transforming into more massive elliptical galaxies or large disk galaxies, while others might be destroyed altogether. One of the more fascinating aspects of the study of faint blue galaxies is their role in shaping our understanding of galactic environments. Galaxies do not exist in isolation. Instead, they are part of a larger, interconnected cosmic web of gas, dark matter, and other galaxies. Faint blue galaxies, being located at the edges of the observable universe, are often found in these web-like structures, giving us a window into how galaxies form and interact within their broader environment. These structures, known as cosmic filaments, act as highways through which matter flows, shaping the way galaxies are distributed and evolve over time. By studying the relationship between faint blue galaxies and the surrounding cosmic web, we can begin to understand how the large-scale structure of the universe has influenced the development of galaxies. Moreover, the light we observe from these distant galaxies is not just a snapshot of their current state, but a record of their interactions with the environment around them. For instance, the process of galaxy formation is influenced by factors such as the density of gas in the surrounding space, the presence of other galaxies, and even the distribution of dark matter. The faint blue galaxies, by virtue of their location and distance, can reveal how galaxies formed in different cosmic conditions. The interplay between gas and dark matter, for instance, is an area of great interest, as it governs the flow of matter into galaxies and influences their growth. The presence of dark matter, in particular, plays a crucial role in the formation of these galaxies. Dark matter, though invisible, exerts a gravitational influence on the surrounding galaxies and helps to shape their structure. In the case of faint blue galaxies, dark matter could be influencing the rate at which gas is funneled into the galaxy, fueling the intense star formation we observe. The role of dark matter in early galaxy formation is still not fully understood, but as we gather more data from these distant galaxies, we may be able to unravel some of its mysteries. Faint blue galaxies also challenge our assumptions about galaxy formation. The prevailing theory has been that galaxies form through a process known as hierarchical clustering, where smaller galaxies merge over time to form larger ones. However, some faint blue galaxies appear to be in a state of rapid star formation without significant prior mergers. This raises important questions about the mechanisms that trigger the birth of galaxies and the factors that control their growth. Are these galaxies the result of isolated pockets of gas that collapse to form stars, or are they the result of interactions with other nearby galaxies? Answering this question will have profound implications for our understanding of how the universe came to be populated with galaxies. Another avenue of research involves understanding the environmental factors that contribute to the evolution of faint blue galaxies. The conditions in which a galaxy forms and evolves are heavily influenced by its environment. Galaxies that are isolated may evolve differently than those that are part of larger clusters or cosmic filaments. The surrounding environment can provide additional gas and materials, fueling star formation, or it can strip away a galaxy's gas, halting star formation altogether. By studying the faint blue galaxies that lie on the edge of the observable universe, scientists can begin to understand how the environment in which a galaxy forms can influence its properties and long-term evolution. The study of these distant galaxies is also closely tied to the study of cosmic inflation, a period of rapid expansion that occurred in the first moments of the universe. Inflation theory posits that the universe underwent an exponential expansion in the first fraction of a second after the Big Bang, smoothing out irregularities and setting the stage for the formation of galaxies and large-scale structures. Faint blue galaxies, observed at such a vast distance, offer a direct look at how this inflationary period may have impacted the formation of cosmic structures. Understanding how the universe went from a nearly uniform state to one filled with galaxies, stars, and other objects is a critical piece of the puzzle in cosmology. As we venture further into the future of astronomical research, the role of faint blue galaxies will only become more pronounced. With the advent of next-generation space telescopes, such as the James Webb Space Telescope and others yet to be conceived, The ability to observe even more distant galaxies will revolutionize our understanding of the early universe. These future observations will provide a clearer, more detailed picture of how galaxies formed and evolved, helping to refine current models of galaxy formation and leading to new discoveries about the fundamental forces that have shaped our universe. The importance of studying these faint blue galaxies also extends beyond just the realm of cosmology. The process of galactic evolution and star formation has implications for our understanding of the origins of life. Stars are the furnaces in which the elements essential for life, such as carbon, oxygen, and nitrogen, are created. By studying the early galaxies where the first stars formed, we can gain insights into the environments that could have been conducive to the development of life. The early universe was a very different place from the one we inhabit today, but it laid the groundwork for the complex processes that eventually led to the formation of planets, stars, and ultimately, life itself. The study of faint blue galaxies at the edge of the observable universe represents one of the most exciting frontiers in modern astronomy. These galaxies provide a glimpse into the very early stages of the universe, offering valuable insights into galaxy formation, star formation, the role of dark matter and dark energy, and the evolution of cosmic structures. As our observational techniques improve, we will continue to peel back the layers of cosmic history, revealing more about the universe's past and its future. The mysteries surrounding these distant galaxies continue to captivate scientists and astronomers alike, and the quest to understand them will undoubtedly lead to new discoveries that deepen our understanding of the cosmos. As we continue to explore the faint blue galaxies scattered at the edges of the observable universe, it becomes evident that they offer more than just a window into the past. They challenge our understanding of the fundamental processes that shape galaxies and the universe itself. The more we learn about these distant objects, the more we realize that they could hold the key to understanding some of the universe's most profound mysteries. While these galaxies may seem distant and disconnected from our daily lives, they are intrinsically tied to our origins and the overall evolution of the cosmos. To fully appreciate the significance of these faint blue galaxies, we need to step back and understand their context in the broader picture of galactic evolution. In the early universe, galaxies formed rapidly, driven by the vast amounts of gas available in the young cosmos. The first galaxies were not the massive, mature systems we see today. Instead, they were smaller, more turbulent, and far more active in terms of star formation. These early galaxies were often chaotic, undergoing frequent mergers and interactions that played a crucial role in their development. As such, the faint blue galaxies we observe at the farthest reaches of the universe represent the early stages of this tumultuous and fascinating period in cosmic history. The stars within these galaxies are often much younger than those in more evolved galaxies like our Milky Way. This is because the galaxies themselves are younger and still in the process of forming. These stars are often referred to as population 2 or population 3 stars. Population 3 stars, in particular, are of immense interest to scientists because they represent the first generation of stars to form after the Big Bang. These stars were composed entirely of hydrogen and helium, the two lightest elements, and lacked the heavier elements produced by previous generations of stars. Studying the remnants of these early stars, such as those found in faint blue galaxies, can provide vital information about the conditions of the universe during its earliest epochs and shed light on the origins of the elements that make up everything we see today. One of the most fascinating aspects of faint blue galaxies is their star formation rate. These galaxies are among the most active in terms of star formation, producing new stars at an astonishing rate compared to more mature galaxies. This intense star formation is often the reason behind their distinctive blue color. The blue hue comes from the hot, young stars that dominate these galaxies. These stars burn through their fuel rapidly, which causes them to shine brightly in the blue end of the spectrum. Over time, as the star formation slows and the young stars die, the galaxy's color shifts from blue to red. This process is a natural part of a galaxy's life cycle and reflects the changing balance between new star formation and the aging of existing stars. In addition to their role in star formation, faint blue galaxies also provide valuable insight into the processes that govern galaxy growth. Many of these galaxies are part of larger structures known as galaxy groups or clusters. These structures play a critical role in shaping the evolution of galaxies. Galaxies and clusters can experience a variety of interactions, such as gravitational interactions and the stripping of gas by the hot gas that pervades the cluster. These interactions can either accelerate or inhibit star formation, depending on the specific conditions of the galaxy and its environment. For instance, a galaxy that passes through a dense region of the cluster may lose much of its gas, effectively halting star formation and turning the galaxy into a red and dead object. Conversely, a galaxy that is not part of a cluster may have access to more gas and experience a more sustained period of star formation. The role of gas in galaxy formation and evolution is one of the most fundamental aspects of understanding faint blue galaxies. Gas, particularly hydrogen, is the raw material from which stars and galaxies are formed. In the early universe, gas was more abundant, and the conditions were conducive to the rapid formation of stars. As galaxies evolve, the gas supply becomes depleted, and star formation slows. The faint blue galaxies we observe are likely still in the process of converting their gas into stars, which is why they appear so blue. As these galaxies evolve and their gas supply is exhausted, they will eventually become redder and less active, similar to the older, more mature galaxies we observe today. An exciting development in the study of faint blue galaxies has been the use of advanced simulations and computer models to recreate the conditions of the early universe. These models help us understand the complex processes that govern galaxy formation, including the interactions between dark matter, gas, and stars. By simulating how faint blue galaxies form and evolve, scientists can test different theories and hypotheses about the underlying mechanisms of galaxy growth. These simulations have provided new insights into the importance of cosmic gas flows, the role of dark matter in shaping galaxies, and how galaxies are influenced by their larger environment. One of the most promising aspects of these simulations is their ability to help us understand the role of feedback mechanisms in galaxy evolution. Feedback refers to the process by which the activity of stars and black holes within a galaxy influences the surrounding environment. For example, the intense radiation and winds from massive stars can blow away gas from the galaxy, reducing the rate of star formation. Similarly, supermassive black holes at the centers of galaxies can produce powerful jets of energy that disrupt the gas in the galaxy, further inhibiting star formation. Understanding how feedback processes work in faint blue galaxies is crucial to our understanding of how galaxies evolve over time. Another important aspect of studying faint blue galaxies is their relationship with dark energy. Dark energy is the mysterious force that is driving the accelerated expansion of the universe. Although we cannot directly observe dark energy, we can study its effects on the large-scale structure of the universe. Faint blue galaxies, by virtue of their position on the cosmic frontier, provide valuable data about the expansion of the universe and the role of dark energy in shaping cosmic structures. By examining how these galaxies are distributed and how their light has been stretched by the expansion of the universe, scientists can learn more about the nature of dark energy and its impact on the universe's growth. The study of faint blue galaxies also intersects with another exciting area of research: the search for life beyond Earth. As we learn more about the conditions that foster the formation of galaxies and stars, we gain a deeper understanding of the environments that might support life. The early universe, when faint blue galaxies were first forming, was a much different place than the one we inhabit today. Yet, the processes that took place in those distant epochs eventually led to the creation of stars, planets, and eventually life itself. By studying the earliest galaxies, we can gain insights into the conditions that might have been conducive to the development of life on other planets and in other galaxies. As we continue to observe these galaxies, it's clear that they are not just remnants of the past but active participants in the ongoing evolution of the universe. The faint blue galaxies we observe today will continue to evolve, merging with other galaxies, forming new stars, and contributing to the cosmic landscape in ways we can't yet predict. Their study is not just about looking back at a distant past but about understanding the processes that will shape the future of the universe. Each new discovery adds a layer of complexity to our understanding of how galaxies form and evolve, And every step forward in this field brings us closer to answering some of the most profound questions about the nature of the universe and our place within it. As technology advances, so too will our ability to explore these galaxies. With the development of next-generation space telescopes and more advanced observational techniques, we will be able to peer even further into the universe's depths and uncover new mysteries hidden in the faint blue light of these distant galaxies. The search for answers is far from over, and as we venture further into the cosmos, we are bound to uncover even more secrets about the early universe and the forces that shaped it. The faint blue galaxies at the edge of the observable universe are far more than just distant objects of scientific curiosity. They are the building blocks of the universe, the first whispers of cosmic evolution, and the key to unlocking many of the greatest mysteries in astronomy. As we continue to study these galaxies and explore their secrets, we are not just learning about the past. We are gaining insights into the very nature of the universe itself, and in doing so, we are uncovering the profound and awe-inspiring story of our cosmic origins. The faint blue galaxies at the edge of the observable universe continue to challenge our understanding of cosmic evolution. Their study not only reveals the formation of stars and galaxies in the early universe but also hints at the very processes that led to the creation of all the structures we observe today. As scientists work to unravel the mysteries of these distant and enigmatic objects, they are discovering that the history of the universe is far more complex and dynamic than we ever imagined. In examining the faint blue galaxies, researchers have uncovered some surprising findings about the distribution and structure of these objects. Unlike the more familiar elliptical or spiral galaxies, these galaxies tend to be irregular in shape, with uneven star formation across their structures. This irregularity may reflect their young age and ongoing evolution, suggesting that they are in the midst of their formative years. Their active star formation is a critical feature that sets them apart from older galaxies, as it highlights a period in cosmic history when the universe was rife with potential for new stars and systems to emerge. This process of active star formation is not without its challenges. The gas that fuels the formation of stars in these faint blue galaxies is often subject to various forces that can either enhance or hinder its ability to condense into new stars. Supernova explosions, stellar winds, and feedback from active galactic nuclei, the bright, energetic centers of galaxies where supermassive black holes reside, can all affect the star formation rate. Despite these challenges, the sheer quantity of gas available in these early galaxies allows for the rapid creation of new stars, which is one of the reasons they appear blue. The intense radiation from these young stars excites the surrounding gas, causing it to emit light at shorter wavelengths, thus producing the distinctive blue glow. Additionally, astronomers have also studied the chemical composition of the stars in these faint blue galaxies. These stars, being among the earliest in the universe, are often composed primarily of hydrogen and helium, with minimal amounts of heavier elements. This composition gives us a glimpse into the conditions of the universe shortly after the Big Bang, when only the lightest elements were formed in the process known as nucleosynthesis. As these galaxies evolve and generate heavier elements through star formation, they will eventually develop the metal-rich composition that is characteristic of more mature galaxies, such as the Milky Way. Studying the chemical composition of these galaxies not only helps us trace the history of the universe's chemical evolution, but also provides insight into how future generations of galaxies may develop over time. Another intriguing aspect of faint blue galaxies is their role in the context of cosmic structure formation. Galaxies are not isolated entities in the universe. They are part of larger cosmic structures such as galaxy groups, clusters, and superclusters. Faint blue galaxies, with their relatively low mass and young age, may play a key role in the ongoing evolution of these structures. Some of the most interesting phenomena observed in these galaxies are the ways in which they interact with their environment. For instance, in galaxy clusters, the immense gravitational pull of the cluster can influence the behavior of individual galaxies, either by pulling them together into mergers or by stripping away their gas supply. These interactions can dramatically alter the course of a galaxy's development and contribute to the formation of larger, more mature galaxies over time. The study of faint blue galaxies also has significant implications for our understanding of dark matter. Dark matter, a mysterious and invisible substance that makes up a significant portion of the universe's mass, has a profound impact on the formation and behavior of galaxies. In fact, it is thought to play a crucial role in the formation of structures in the universe, providing the gravitational scaffolding that allows galaxies to form and evolve. While we cannot directly observe dark matter, we can study its effects on the motion of galaxies and other cosmic objects. By examining the motion and distribution of faint blue galaxies, scientists can gain valuable insights into the properties of dark matter and its role in shaping the universe. As we continue to explore these distant galaxies, we are also uncovering clues about the fate of the universe. The faint blue galaxies are relics of an earlier epoch in cosmic history, and their study offers a window into the processes that will shape the future of the universe. These galaxies will eventually evolve into more mature, redder galaxies, marking a transition from the vigorous, star-forming phase of their existence to a more stable and quiescent state. This transition is part of a larger cosmic cycle that has been ongoing since the Big Bang. In fact, by studying the life cycles of galaxies like these, scientists can learn more about the long-term evolution of the universe, from its earliest moments to its eventual fate. One of the most exciting aspects of studying faint blue galaxies is the potential for new discoveries. With the development of new telescopes and observational techniques, we are now able to peer deeper into the universe than ever before. Instruments like the James Webb Space Telescope, JWST, are opening up new frontiers in our understanding of distant galaxies, providing unprecedented detail about their structure, composition, and evolution. These advances in technology are allowing us to observe the faint blue galaxies in greater detail, uncovering new aspects of their properties and behavior that were previously hidden from view. The JWST, in particular, is poised to make groundbreaking contributions to our understanding of the early universe. With its ability to observe infrared light, the JWST will allow us to study galaxies that are far beyond the reach of previous telescopes. By detecting the faint light from galaxies that formed shortly after the Big Bang, we will be able to explore the conditions that gave rise to the first galaxies and stars. This could provide critical insights into the origins of galaxies like the faint blue galaxies we observe today, and help us understand the processes that led to the formation of the larger, more complex galaxies we see in the present. As we continue to study these faint blue galaxies, we are also gaining a deeper understanding of the nature of the universe itself. The observation of galaxies at the farthest reaches of the observable universe allows us to probe the very limits of space and time. These galaxies are not just distant objects, they are time machines that offer a glimpse into the universe as it was billions of years ago. By studying their light, we are looking back in time to an era when the universe was in its infancy, and the processes that would eventually lead to the formation of stars, galaxies, and life itself were just beginning to unfold. This ability to observe the past in such detail is one of the most powerful tools at our disposal as we seek to understand the universe. It allows us to piece together the story of cosmic evolution, from the Big Bang to the present day, and offers a unique perspective on the forces that have shaped the cosmos. The faint blue galaxies are an essential part of this story, serving as both the building blocks of the universe and the key to unlocking its deepest secrets. The study of faint blue galaxies at the edge of the observable universe is a journey into the very heart of cosmic history. These galaxies are not just distant and faint objects, they are the seeds from which the universe has grown and evolved. By understanding their formation, evolution, and interaction with the larger cosmic environment, we gain insights into the very nature of the universe itself. The mysteries they contain are not just scientific curiosities, they are the keys to understanding the past, present, and future of the cosmos, and in doing so, they help us answer some of the most profound questions about our place in the universe. As the faint blue galaxies continue to capture the imagination of astronomers and astrophysicists, they offer more than just a look into the early universe. They also present opportunities to test some of the most fundamental theories of cosmology. These galaxies are often used to probe ideas about dark energy, the accelerating expansion of the universe, and the physics of star formation in the extreme environments of the distant cosmos. One of the most significant discoveries in recent years has been the realization that these faint blue galaxies are much more common than previously thought. For many years, scientists believed that galaxies in the distant universe were more massive and structured than they appear to be today. The discovery of a large number of these faint blue galaxies at the edges of the observable universe has forced cosmologists to reevaluate their models of galactic evolution. It suggests that the universe may have followed a different path in its early stages than previously understood, with smaller, less massive galaxies playing a much larger role in the formation of cosmic structures. This finding also has implications for our understanding of galaxy mergers and the role they play in shaping the universe. As galaxies evolve, they often collide and merge with one another, leading to the formation of larger, more complex systems. The faint blue galaxies that we observe at the edges of the universe may have been among the first to undergo such mergers, with their smaller, irregular shapes providing fertile ground for the creation of more mature galaxies. This process is thought to have been a crucial step in the formation of the large, well-defined galaxies that populate the universe today. The study of faint blue galaxies also sheds light on the ways in which the universe has changed over time. When we observe these distant objects, we are seeing them as they were billions of years ago, before many of the processes that define present-day galaxies took place. This allows us to observe the very early stages of galaxy formation, a time when the universe was still in its infancy. By comparing these galaxies to their more evolved counterparts, we can track the changes that have occurred over cosmic time scales and learn about the forces that have shaped the universe. In addition to the study of galactic evolution, the faint blue galaxies also offer a unique opportunity to probe the nature of the intergalactic medium, the vast, mostly empty space that exists between galaxies. The gas in this medium, known as the intergalactic medium, IGM, plays a crucial role in the formation and evolution of galaxies. By studying the light emitted by faint blue galaxies as it passes through this gas, astronomers can gain valuable insights into the properties of the IGM and its role in the development of cosmic structures. One of the key aspects of the intergalactic medium is its composition. The IGM is made up primarily of hydrogen and helium, with trace amounts of heavier elements. This composition provides clues about the early universe, when the first stars and galaxies were forming. As these stars and galaxies began to shine, they ionized the surrounding gas, creating what is known as the epoch of reionization. The study of faint blue galaxies allows us to explore this era in greater detail, as these galaxies were among the first to light up the universe after the Big Bang. The presence of certain types of gas in the IGM can also reveal information about the processes that occurred during the formation of galaxies. For example, the discovery of certain metal-enriched regions in the IGM suggests that star formation was occurring in these distant galaxies long before we previously thought. These regions of metal-enriched gas may have been produced by the death of the first generations of stars, which released heavy elements into the surrounding space. Understanding how these metals spread through the IGM is crucial to understanding the chemical evolution of the universe. Another exciting possibility is that the study of faint blue galaxies could provide clues about the mysterious nature of dark energy. Dark energy is the term used to describe the mysterious force that is driving the accelerated expansion of the universe. While we know that dark energy exists, we have very little understanding of what it actually is or how it operates. By studying the distribution of faint blue galaxies and their relationship to the expansion of the universe, astronomers may be able to gain valuable insights into the nature of dark energy and its role in the future of the cosmos. The rapid expansion of the universe, coupled with the distant location of these faint blue galaxies, also raises important questions about the structure and geometry of space itself. In the distant past, the universe was much smaller and denser, and as it expanded, space itself stretched, causing the wavelengths of light from distant galaxies to shift toward the red end of the spectrum. This phenomenon, known as redshift, allows astronomers to measure the distance to galaxies and estimate their age. However, the light from the faint blue galaxies is even more redshifted, making them some of the most distant objects we can observe. This extreme redshift makes the study of these galaxies particularly challenging, as the light we see from them has been stretched to such an extent that it is difficult to detect. This is where advanced observational techniques, such as the use of spectrometers and powerful telescopes, come into play. Instruments like the Hubble Space Telescope, and more recently, the James Webb Space Telescope, are essential tools for studying these distant galaxies in greater detail. These telescopes allow scientists to capture the faintest of light from these galaxies, even from distances that would have been previously impossible to observe. The detailed observations of faint blue galaxies provide a wealth of information about their properties, from their size and shape to their chemical composition and star formation rates. But it also offers a broader perspective on the universe as a whole. By understanding the processes that govern the formation and evolution of these galaxies, we are essentially studying the forces that have shaped the universe since the very beginning. In this sense, the study of faint blue galaxies is not just about understanding individual objects in space. It is about unraveling the story of the universe itself. As we look forward to the next generation of space telescopes and observational technologies, the study of faint blue galaxies will undoubtedly continue to be at the forefront of astronomical research. These galaxies are among the most distant and primitive objects we can observe, and they hold the key to understanding the earliest moments of cosmic history. The insights we gain from studying them will not only deepen our understanding of the universe's past but also provide crucial clues about its future. The faint blue galaxies at the edge of the observable universe represent a cosmic frontier, a place where the past, present, and future of the universe converge. These galaxies are the distant echoes of the Big Bang, the first light of a universe still in its infancy. As we continue to study them, we are not just uncovering the history of galaxies, we are uncovering the history of the universe itself. And in doing so, we may come closer to answering some of the most profound questions about the cosmos and our place within it. As we continue to delve into the study of these faint blue galaxies, it's important to recognize how far we've come in our technological advancements. The early days of astronomical observation relied on simple telescopes and the naked eye, which were often limited in their ability to detect objects as distant and faint as the blue galaxies at the edge of the observable universe. Now, with the advent of modern space telescopes like Hubble, and the anticipated capabilities of the James Webb Space Telescope, JWST, our ability to observe these distant objects has grown exponentially. These advancements in technology have enabled us to probe the faintest and most distant galaxies, ones that may have been invisible to earlier generations of astronomers. The launch of JWST, in particular, marks a monumental leap in our ability to study the far reaches of the universe. JWST's powerful infrared capabilities allow it to observe the faint blue galaxies in greater detail than ever before, even as the light from these galaxies has traveled billions of years to reach us. As we peer deeper into space and time, we are uncovering new layers of the cosmic puzzle. In many ways, the study of these faint blue galaxies is an exploration into the early universe. Every new discovery about these distant objects provides a snapshot of what the universe was like in its infancy. These galaxies formed within the first few billion years after the Big Bang, during a time when the universe was still in a state of rapid expansion and transformation. By studying the composition, structure, and behavior of these galaxies, scientists are able to piece together a more detailed picture of the universe's early stages, a time when stars and galaxies were beginning to take shape. One of the most intriguing aspects of these faint blue galaxies is the way they challenge our previous assumptions about galactic evolution. Prior to the discovery of these distant galaxies, it was believed that the process of galaxy formation was largely driven by the merging and accretion of gas and matter over time. While this process certainly plays a significant role in the evolution of galaxies, the faint blue galaxies at the edge of the observable universe suggest that the formation of galaxies may have been more diverse and complex than we initially thought. These faint blue galaxies are often smaller, irregularly shaped, and less evolved than many of their more mature counterparts. Their blue color indicates that they are still in the process of forming stars, suggesting that they are relatively young and have not yet had the time to develop into the large, well-defined structures that we observe in the present-day universe. This discovery has led scientists to propose that smaller, less massive galaxies played a significant role in the early stages of galaxy formation, potentially even predating the larger, more structured galaxies that dominate the cosmos today. The study of these galaxies also raises important questions about the nature of dark matter, the invisible substance that makes up a large portion of the universe's mass. Dark matter is thought to exert a gravitational influence on galaxies, helping to shape their structure and prevent them from disintegrating as they rotate. However, the exact nature of dark matter remains one of the greatest mysteries in modern cosmology. By studying the distribution of galaxies in the early universe, including these faint blue galaxies, scientists hope to gain new insights into how dark matter influences galaxy formation and evolution. The faint blue galaxies are also a valuable tool for studying the phenomenon known as cosmic reionization. This process refers to the period in the universe's history when the first stars and galaxies began to emit light, ionizing the surrounding hydrogen gas and making it transparent to ultraviolet radiation. Understanding when and how reionization occurred is crucial for understanding the evolution of the universe, as it marks the point when the universe transitioned from being opaque to transparent. The faint blue galaxies, with their young, star-forming properties, provide a window into this important era. As scientists continue to explore these distant galaxies, they are also uncovering new mysteries about the intergalactic medium, the vast, mostly empty space between galaxies. The gas that fills this space, known as the intergalactic medium, IGM, is crucial for understanding how galaxies form and evolve. The faint blue galaxies, being some of the most distant objects we can observe, allows scientists to study how the IGM interacts with the light emitted by galaxies in the early universe. This provides important information about the composition and behavior of the gas that fills the space between galaxies. In particular, the IGM is thought to play a significant role in the process of galaxy formation. As gas accumulates in these distant galaxies, it provides the raw material for star formation. The presence of certain elements, such as hydrogen and helium, in the IGM can also reveal important details about the conditions in the early universe. By studying the light emitted by faint blue galaxies as it passes through the IGM, astronomers can gain insights into the properties of this gas and its role in the development of cosmic structures. The relationship between the IGM and the faint blue galaxies also provides valuable clues about the nature of the universe's large-scale structure. The distribution of galaxies across the cosmos is not random but follows a complex pattern influenced by gravity, dark matter, and other forces. By studying the spatial distribution of faint blue galaxies, scientists can learn more about the large-scale structure of the universe and how it evolved over time. This knowledge is key to understanding the forces that shape the cosmos and continue to influence its evolution. Another fascinating aspect of these faint blue galaxies is the potential they hold for advancing our understanding of dark energy. As previously mentioned, dark energy is the mysterious force that is causing the accelerated expansion of the universe. While dark energy is thought to account for about 70% of the universe's total energy content, its exact nature remains unknown. The study of faint blue galaxies, particularly in relation to their distribution and redshift, may help scientists to better understand how dark energy affects the expansion of the universe and how it has evolved over time. The role of dark energy in the expansion of the universe is a subject of intense research and debate. Some scientists believe that dark energy is responsible for the observed acceleration in the rate of expansion, while others argue that it may be a manifestation of a more fundamental property of space itself. By studying faint blue galaxies, astronomers can test different models of dark energy and gain new insights into how this mysterious force operates on cosmic scales. As we look forward to the future of astronomical research, the study of faint blue galaxies will continue to be an area of great interest and excitement. New telescopes and observational techniques will allow scientists to probe even deeper into the distant universe, uncovering new mysteries and providing valuable data to refine our understanding of the cosmos. Whether it's exploring the nature of dark energy, examining the early stages of galaxy formation, or probing the intergalactic medium, the faint blue galaxies at the edge of the observable universe are sure to remain a key focus of cosmological research for years to come. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.